Hello there, and welcome to Life Beyond Seen, where curiosity settles down, the strange parts of the world become a little quieter, and science takes the long road towards sleep. Tonight, we're going somewhere warm, green, and full of holes in the ground, which is not usually how a relaxing journey begins, but in this case, it works rather well. We are travelling to the Yucatan Peninsula in Mexico, a place where the jungle looks solid from above, but underneath it the land is not solid in the way you might expect. Beneath the trees, roads, roots and old stone ruins, there is another world. It is a world of flooded caves, hidden rivers, narrow passages, wide blue chambers and deep sinkholes called cenotes. Some are open to the sky, bright and calm, with vines hanging down the sides and sunlight resting on the water. Others are almost completely hidden, tucked inside caverns where the air is cool, the walls are pale limestone, and the water is so clear that divers sometimes feel as though they are floating through glass. At first, a cenote can look simple. A pool in the jungle, a natural well, a quiet place where people swim, birds drink, and sunlight moves in slow shapes across the surface. But that is only the entrance. Below that surface, the water may lead into tunnels that run far beyond the pool itself. Some of these tunnels twist for miles. Some connect to other cenotes. Some pass through rooms filled with ancient bones, stone tools, mineral formations, and traces of people and animals that entered when the caves were dry, long before the sea rose and filled them. Some passages are mapped, many are not. And a few still leave scientists, divers, archaeologists and geologists with questions that do not yet have simple answers. Not questions like, who built these? Because the tunnels were not built by human hands. They were shaped by water, limestone, time, sea level changes, and chemistry doing very slow work. But questions like, exactly how far do they go? Why do some passages connect in ways that seem almost impossible from the surface? How did ancient remains end up so deep inside certain chambers? What else is preserved in the dark? How does fresh water move through these hidden routes? And perhaps most quietly of all, how much of this underground world have we still not seen? That is the part that makes the Yucatan cenotes so fascinating. They are not unexplained in the sense of a magic trick. They are unexplained in the more interesting sense. We know enough to understand that they belong to geology, chemistry, archaeology, ecology and history. But the more carefully people study them, the more details appear. A cave diver follows a passage that seems to end, then finds a small opening, then another chamber, then another line of tunnel disappearing into black water. A scientist studies the water and finds layers of fresh and salty water sitting on top of each other, not quite mixing, as if the cave has its own quiet rules. An archaeologist examines a submerged chamber and realizes that what now lies deep underwater may once have been a dry place where humans walked, rested, hunted, or performed rituals. A geologist looks at a map of cenotes from above and sees a strange ring, a pattern in the land that points back to one of the most violent events in Earth's history. So tonight's journey is not just about pretty pools in the jungle, though they are certainly pretty. It is about the secret architecture under Yucatan. It is about water moving where there are no surface rivers. It is about tunnels that can look still and silent, while quietly carrying the drinking water of entire communities. It is about the ancient Maya, who treated many cenotes as sacred places and sometimes as entrances to the underworld. It is about bones left in darkness, creatures that live without sunlight, divers who move carefully through passages where the ceiling is stone and the way out may be far behind them. It is about how much of Earth can remain hidden directly below our feet, even in places that people visit every day wearing sandals, carrying towels, and wondering whether they remembered sunscreen. Before we go farther, let me ask you something simple. Where are you listening from tonight? Are you somewhere near the sea, somewhere inland, somewhere cold, somewhere warm, or perhaps somewhere very ordinary that feels a little less ordinary now that we are, thinking about hidden water under the ground. And if you can imagine standing at the edge of a cenote in the Yucatan, looking down into clear blue water, would you want to swim straight in? Or would you stay at the edge for a while and let your eyes adjust first? There is no wrong answer. Some people look at deep water and feel peaceful. Others look at it and immediately remember that we are land animals with poor night vision and no built-in flotation system. Both reactions are understandable. The cenotes have that effect. They invite you closer, but they also remind you that the world is much larger than the part we can see from the path. If you find this kind of quiet exploration soothing, and if you enjoy science that does not shout at you, I would be very grateful if you gave the video a like and subscribed. It helps this calm little corner of the internet reach other people who may also like their mysteries served gently, with facts, soft humour, and only a small chance of imaginary cavefish watching from the darkness. And if you are already settled in, perhaps with the lights low, or with the room quiet, or with one ear listening while the rest of you slowly considers sleep, then you are in exactly the right place. Now, let us begin at the surface. Picture the Yucatan from above, not as a political map, not as a tourist brochure, but as land. A broad, low peninsula reaching between the Gulf of Mexico and the Caribbean Sea. Much of it is made of limestone, which is important because limestone behaves very differently from harder rock. It does not simply sit there forever, refusing to participate. Limestone can be dissolved by slightly acidic rainwater. Drop by drop, year after year, water seeps into cracks, widens them, follows weaknesses, opens pockets, and eventually creates caves. Not quickly, of course. Limestone is not in a hurry. It works on a schedule that would make a mountain seem impatient. The result is a karst landscape, which is a useful scientific term for land shaped by dissolving rock. Karst regions often have sinkholes, caves, underground drainage, and very few surface rivers. In Yucatan, that last part matters a great deal. In many places, you do not see big rivers winding across the surface because the water has gone underground. Rain falls, filters through thin soil, slips into the limestone and joins a vast hidden aquifer, so the land may look dry above, while underneath it is full of water moving through cracks and chambers. That is one reason cenotes became so important to people living there. In a landscape without easy surface rivers, a cenote is not just scenic, it is access. It is a way into the aquifer. It is a water source, a landmark, a gathering place, and in the Maya world, often something more than practical. A cenote could be a sacred place, a place linked with rain, fertility, offerings, ancestors, gods, and the underworld. When you stand beside one, you're not just looking at water, you're looking at the meeting point between daily life and deep time, which sounds dramatic but also very accurate. It is hard to be casual about a hole in the ground that may connect to miles of dark flooded passage. The word cenote comes from the Maya word often written as zonot or zonoot, referring to a natural well or water-filled cavity, and there are many kinds. Some cenotes are open, like round pools where the roof has fully collapsed. Some are semi-open, with part of the cave ceiling still covering the water. Some are almost closed, entered through a small opening into a chamber below. Some have stairs built for visitors. Some require ropes. Some are famous and busy, filled with swimmers and cameras. Others are known mostly to local communities, researchers, or cave divers who understand that the most important rule underground is not bravery. It is respect. Because underwater caves are not like ordinary swimming spots. A clear pool can hide a complex system underneath. The water may be fresh near the top, then become salty deeper down. The passage may be wide enough to move through comfortably, then narrow into a restriction where a diver must pass slowly, carefully, with equipment close to the body. A beam of light may reach the entrance, then disappear behind the first bend. After that, the cave becomes a place where every movement matters. Divers use guideline reels so they can find their way back. They monitor gas carefully. They move slowly too, Avoid stirring sediment from the floor because one careless fin kick can turn perfect visibility into a cloudy white wall. It is not a place for guessing. The cave has very little interest in human confidence, and yet people go in. Carefully trained cave divers go in because these tunnels hold information that cannot be found from the surface. They map routes, collect samples, photograph formations, document bones and artifacts, and help scientists understand the underground water system. In the Yucatan, cave diving is not just adventure. It is exploration in the old sense of the word. The kind where a map may still have blank spaces and where progress can mean tying a line through a passage no one has recorded before. One of the strange things about these caves is that they can feel both ancient and active. The walls formed over enormous spans of time, but the water inside them is not frozen in the past. It moves. It responds to rain, tides, storms, drought, sea level, and human activity above. A cenote that looks peaceful may be connected to water flowing under towns, roads, forests, and coastlines. Contamination can move through karst quickly because the rock is full of openings rather than thick layers that filter everything slowly. That means the cenotes are beautiful, but also vulnerable. They are windows into the aquifer, and windows can let things in. This is part of the reason scientists care so much about them. The mystery is not just where the tunnels go, it is how the whole system works. How does fresh rainwater move through the peninsula? Where does it meet salt water from the sea? How fast does it travel? Which cenotes are connected? Which passages carry the most flow? Which areas are most at risk from pollution? These questions may sound less dramatic than ancient bones or underwater caverns, but they matter deeply. A hidden river is still a river, even if tourists are not taking boat rides on it. And if that hidden river is part of the freshwater supply, then understanding it is not optional. It is the difference between treating the landscape as scenery and treating it as a living system that people depend on. Then there is the matter of the caves themselves. Many of the underwater tunnels in Yucatan were not always underwater. During parts of the Ice Age, sea levels were lower, and some cave systems that are now flooded were dry. Animals could enter. Humans could enter. Mineral formations could grow in air. Stalactites and stalagmites formed slowly from dripping water, the same way they do in dry caves elsewhere. Later, as ice melted and sea levels rose, water moved in and drowned the passages. What had once been a dry cave became an underwater time capsule. That is why divers sometimes find remains in places that seem impossible at first glance. A skeleton deep in a flooded cave may not mean someone swam there. It may mean the cave was dry when that person or animal entered thousands of years ago. A chamber that now requires tanks, lights, and technical training may once have been reached on foot, perhaps with a torch, perhaps by accident, perhaps with purpose. The water arrived later and preserved what the dry world left behind. This is where these cenotes become especially quiet in the mind, because they are not only geological features, they are archives. They preserve bones of extinct animals. They preserve traces of ancient humans. They preserve chemical clues about past climates and sea levels. They preserve the shapes of passages carved by water long before anyone named them. They also preserve questions, not because scientists are helpless before them, but because careful science often begins by admitting that the first answer is not enough. For example, when remains are found deep inside a cave, researchers may ask how they got there. Was it an accident? A fall? A burial? A ritual placement? Did the cave entrance look different then? Was the chamber dry? Was it easier to reach? What was the surrounding landscape like at that time? Each answer depends on geology, archaeology, dating methods, sediment, bone position, and the cave's own history. The story is not sitting there with a label attached. It has to be reconstructed piece by piece. The same is true of the tunnels. On a map, the underwater cave systems can look like tangled roots, spreading beneath the peninsula in long pale lines. But unlike tree roots, they are not easily visible. They must be explored, metre by metre. A passage may be large enough to swim through, then blocked by collapse. Another may open behind a restriction. A cenote may connect to a system already known, or it may lead to a separate network. Sometimes two famous systems are discovered to be part of a larger connected whole, changing the map and the rankings of the world's longest underwater caves. Somewhere, beyond the last surveyed line, there may be another room, another tunnel, another entrance, another clue. This is probably why the phrase underwater tunnels scientists still can't explain catches the imagination. It suggests something dramatic hiding below the jungle. And in fairness, there is drama there. But the real wonder is better than a simple mystery headline. The real wonder is that these tunnels are explainable and still not fully explained. We understand many of the processes that formed them, but not every passage. We understand the broad geology, but not every connection. We know that ancient people used cenotes, but not the full meaning of every object or remain found in them. We know that water moves through the aquifer, but not every route it takes on every day of every season. The unknown is not a blank wall, it is a partly drawn map. And that is often how science actually feels. Not like standing before a locked door with no key, but like walking through a large old house where some rooms are lit, some are dark, and some doors open into hallways no one expected. You do not need to invent monsters to make it interesting. The limestone, the water, the bones, the maps, the chemistry and the silence are enough. So tonight we will move slowly. We will begin with the cenotes themselves, these blue openings where the land gives way to water. We will look at how the Yucatan became a place of hidden rivers. We will follow the story back to the asteroid impact that left a buried scar beneath the peninsula and may have helped shape the famous ring of cenotes. We will enter the long underwater systems, including passages that stretch for hundreds of kilometres when mapped together. We will pause at the halocline, where fresh water and salt water meet in a shimmering layer that can make the world look suddenly blurred. We will consider the bones, offerings and ancient remains preserved below. We will talk about Maya beliefs, not as decoration, but as part of the human relationship with these places. We will meet small animals adapted to darkness, and finally, we will drift toward the unmapped passages still waiting beyond the last line. For now, imagine standing at the edge of one cenote just after sunset. The heat of the day is fading. The jungle is making its evening sounds. The water below is still enough to reflect the opening above, so for a moment it looks as though the sky has fallen into the ground and decided to stay there. A few leaves rest on the surface. Somewhere below them, the pool deepens. Beyond the blue circle, a tunnel begins. The first meters are visible, then the light thins, then the passage turns away. That is where our story enters. Not with a rush, not with a splash, but with a careful look downward, into the clear water, toward the place where the surface world ends and the hidden one begins. From the edge of the water, a cenote can seem almost too simple to explain. There is a hole in the limestone, there is water at the bottom. There may be a few stone steps, a wooden platform, a rope for swimmers, a sign asking people not to wear sunscreen before entering, and perhaps a small group of visitors standing there with towels, looking down and deciding whether the water is going to be pleasantly cool or personally insulting. But the longer you look, the less simple it becomes. A cenote is not just a pond that happened to appear in the jungle. It is usually the visible opening of a much larger underground system. The pool you see from above may be the top of a flooded chamber. That chamber may connect to a tunnel. The tunnel may connect to another cenote, and then another, and then a passage where no daylight reaches at all. From the surface, it may look like a quiet circle of water. Underneath, it can be part of a complicated network that carries fresh water through the limestone like plumbing designed by geology, and then left unfinished for several million years. The Yucatan Peninsula is especially good at making these openings because so much of it is made of limestone. Limestone is a sedimentary rock, formed mostly from the remains of ancient marine organisms that lived in warm, shallow seas. That alone is a useful thing to remember. When you walk through parts of Yucatan, you're walking over old seafloor. The land is not only land, it is a raised piece of a former marine world, packed with carbonate rock, shells, minerals, old reef material, and the slow record of oceans that are no longer there. Limestone has one important weakness. It dissolves in slightly acidic water. Rainwater becomes weakly acidic as it absorbs carbon dioxide from the air and from soil. It does not become dangerous acid, of course. It is not going to hiss through your shoes like something from a laboratory accident. It is gentle. It is ordinary. It is the kind of water that falls on leaves, drips from branches, and disappears into the ground without making any announcement. But give that water enough time, and it can widen cracks in limestone. It can open small spaces into larger spaces. It can turn hidden fractures into channels, pockets, caves, and eventually caverns. This is how karst landscapes form. A karst landscape is not carved mainly by rivers flowing across the surface, but by water working through soluble rock underneath. In some parts of the world, karst creates dramatic towers and cliffs. In others, it creates caves, sinkholes, springs, and underground drainage. In Yucatan, the result is a broad, low landscape where much of the water does not stay on top of the land for very long. Rain falls, it filters down, it enters the limestone, it joins the groundwater. Instead of a neat blue river winding across the surface, there are many hidden routes below. That is why cenotes mattered so much, long before anyone arrived with diving lights or waterproof cameras. In much of northern Yucatan, there are few permanent surface rivers. If you need water, and of course every settlement needs water, you need access to the aquifer. A cenote gives you that access. It is a natural well, and for the people who live there, it could mean survival. Drinking water, cooking water, water for crops, animals, ceremonies, washing and daily life could all depend on these openings. Imagine living in a hot limestone region, where the rain may come in heavy seasonal bursts, but the surface does not hold rivers the way other landscapes do. You learn the locations of the cenotes. You remember which ones are deep, which ones are clean, which ones are difficult to reach, which ones belong to certain communities, which ones should be treated carefully. A cenote becomes more than a useful place. It becomes a known point in the land, a reference, a meeting place, a dependable source, the difference between a hard dry season and one that can be managed. This practical importance helps explain why many Maya cities and settlements were placed near cenotes or other reliable water sources. Chichen Itzá, one of the best-known Maya cities, had important cenotes nearby. The name itself is often explained as connected with the mouth of the well of the Itzá. That is not a small detail. It tells you that the water was not just background scenery. It was part of the identity of the place. Still, it would be a mistake to treat cenotes only as useful wells. They were also meaningful places. In Maya thought, caves, openings in the earth, and bodies of water could be connected with the sacred. Some cenotes were associated with offerings and ritual activity. To modern eyes, it can be tempting to separate things very cleanly. This pool is practical, that temple is sacred, this object is ordinary, that one is ceremonial, but ancient life was often not arranged in such tidy folders. A place could be useful and sacred at the same time. Water could be something you needed to drink and something connected with rain, fertility, ancestors, gods, and the world below. This is part of what gives the stone wells of Yucatan their deep human pull. You can stand at the edge of one today, hearing people laugh as they climb down to swim, and you can also know that for centuries these openings were approached with a different kind of attention. Not necessarily with fear, not only with worship, but with awareness. The cenote was not a swimming pool, it was an entrance, it was a source, it was a place where the visible world touched the hidden one, and physically, that is exactly what it is. The cenote often begins as a cave or cavity below the surface. Water dissolves the limestone. Voids grow. The roof may become thinner or weaker. At some point, a collapse can happen, and the ceiling gives way. The groundwater below is exposed. The result is a sinkhole filled with clear water. Some cenotes have sheer vertical walls like wells cut into stone. Some are broad and open. Some are almost cave-like, with only a small opening overhead. Some are old, where erosion has widened the opening and softened the edges. Others are younger and more enclosed, with a roof still partly intact. If you visit several cenotes, you quickly notice that they do not all feel the same. An open cenote can feel bright and social. Sunlight reaches the water directly. Plants grow along the rim. Birds come and go. The surface may sparkle in a way that makes everyone suddenly interested in taking photographs of themselves looking thoughtful. A semi-open cenote feels different. There may be a large chamber with one part of the roof collapsed, so light enters from above in a column. The air inside is cooler. Sounds echo. The water can look blue, green, or black depending on depth and light. A cave cenote feels different again. You enter through a narrow passage or down steps into a dim room, and the water waits below under stone. It is still beautiful, but the beauty has more weight to it. You are aware of the ceiling. That awareness matters because the ceiling is part of the story. Every open cenote is evidence that stone once failed. Not dramatically in the way we imagine a building collapsing, but geologically. A void grew beneath the surface. The roof could no longer support itself. Then the sky entered. That is why the phrase "stone wells that swallowed the sky" fits these places so well. A cenote can look like a piece of sky has been placed underground. In the middle of the day, when sunlight reaches the water, the blue can be startling. It is not always the blue of the sea. It can be clearer, colder, more transparent. In some cenotes, you can see fish below you and rock ledges descending into the depth. In others, you look down and the water darkens quickly. It is not dirty. It is simply deep or shaded or connected to a chamber that keeps its details to itself. Visitors often talk about how clear cenote water is. That clarity is not magic. It comes from filtration through limestone and from the fact that many cenotes are connected to groundwater rather than muddy surface runoff. But clear water can be deceptive. It can make depth hard to judge. A pool that looks shallow may be much deeper than expected. A ledge may appear close enough to touch and actually be several meters away. Divers know this very well. Clear water can feel welcoming, but it can also remove some of the visual cues humans usually rely on. Your brain looks down and says, "That seems manageable," which is exactly the sort of statement that has caused problems for human beings since the beginning of time. The first people who used cenotes did not need a modern geology textbook to understand that these places were special. They saw the practical reality every day. In a region where water moved underground, these wells gave access to life. But they also saw the strangeness. The land opened. Cool air rose. Water sat in the dark. Sounds changed near the rim. Birds and bats moved in and out. Roots reached down the stone walls. In some places, the water was so far below the surface that reaching it required effort, tools, or built access. A person approaching such a place would know they were not simply walking to a stream. Some cenotes became associated with offerings because water itself was tied to survival. The Maya rain god Shak was deeply important in a region where rainfall patterns mattered, and drought could be dangerous. When people made offerings in cenotes, they were not behaving randomly. They were interacting with places that seemed connected to the forces that controlled water, rain, and the world beneath the surface. Archaeologists have recovered objects from some cenotes, including ceramics, ornaments, and in certain famous cases, human remains. Those finds have to be studied carefully. Not every object in a cenote has the same meaning. Some things fall in by accident, some are washed in, some may be placed deliberately, some may come from later periods. The water preserves, but it does not automatically explain. That is one of the reasons cenotes continue to be so valuable to researchers. They are not single-purpose sites. They are geology, water supply, ecosystem, archaeological archive, and cultural landscape all at once. A scientist studying them has to think in several directions. The shape of the sinkhole tells one story. The chemistry of the water tells another. The sediments at the bottom tell another. A pot, bone, or tool tells another. The local traditions around the place may tell another still. Cenotes do not give up their meaning in one sentence. Even their formation can vary more than the simple version suggests. Yes, many are formed when limestone collapses and exposes groundwater. That is the basic explanation. But the underground spaces that collapse may have developed in different ways depending on fractures, water flow, sea level, and the mixing of fresh and salt water. The Yucatan aquifer is coastal, which means seawater can intrude beneath the freshwater lens. Fresh water, being less dense, tends to sit above salt water. Where the two meet, chemical reactions can increase dissolution in the limestone. This can help enlarge caves at certain depths. So the caves are not just holes made by water in a general sense. They're shaped by very particular conditions, including the chemistry of mixing waters. That becomes important later when we follow the tunnels beyond the wells. For now, it is enough to picture the cenote not as an isolated pool, but as a window into a layered water system. Rainwater enters from above. Fresh groundwater moves through the rock. Salt water may push in from the coast below. Between them, the limestone slowly changes. Passages widen, chambers form, roofs weaken, some collapse. A cenote appears at the surface, and everyone standing nearby acts as though the hole just happened to be there, when really it is the visible result of an underground process that was working long before anyone had an opinion about sandals. This also helps explain why there are so many cenotes across the region. The Yucatan is not a place with one mysterious sinkhole. It is a landscape full of them. Estimates vary, and not all cenotes are mapped or publicly known, but the number is commonly described in the thousands. Some are famous tourist sites, some are small and local, some are hidden on private land, some are connected to large cave systems, others are isolated or not yet fully studied. A map of cenotes can look at first like scattered dots. Then patterns begin to emerge, especially in the northern peninsula, where a famous arc or ring of cenotes has been linked with the buried structure of the Chicxulub impact crater. But that wider story belongs to the next movements of our journey. For the moment, the important point is simpler. The land is full of openings because the land is full of soluble stone, hidden water, and time. And time is doing a great deal of work here. When a cenote roof collapses, it may feel like a sudden event, but it is usually the final moment of a long preparation. The rock has been weakened by dissolution. Cracks have widened. The cave chamber has grown. The load above has remained. The system has changed little by little until the ceiling can no longer hold. Then, perhaps after a storm, perhaps after gradual erosion, perhaps without anyone nearby to see it, part of the roof falls. What had been sealed underground is now open to air. After that, the cenote keeps changing. The walls weather. Plants colonize the rim. Roots find cracks. Animals arrive. Sediment falls in. People may build steps, platforms, paths, or pumps. In some places, the opening widens over long periods. In others, it remains steep and well-like. A cenote is not a finished object. It is a stage in a process. That may sound calm when said slowly, but it is worth remembering that sinkholes can also be hazardous. In karst landscapes, the ground may hide cavities. Collapse is part of the natural system. Modern construction, heavy loads, groundwater changes and vibration can make this more complicated. The cenotes that look so peaceful in photographs belong to a type of landscape that requires care. The same geology that makes clear pools and underwater caves can also make the ground unpredictable. Limestone gives, but it does not always give warning. In Yucatan, the relationship between people and cenotes is still active. Many communities depend on groundwater. Tourism brings attention and income, but also pressure. Swimming development, roads, waste, agriculture, and large infrastructure projects can affect water quality and cave stability. Because karst systems can transmit water quickly through openings, pollution may not stay politely where it begins. It can move. It can enter the aquifer. A cenote that looks clean at the surface may still be part of a system receiving contamination from somewhere else. This is one reason local groups, scientists, cave divers, and environmental advocates often speak strongly about protecting these places. They are not only beautiful holes in the ground, they are part of the region's water supply. There is a quiet irony in that. Cenotes are famous partly because they look timeless. A person can stand at the edge and imagine the ancient past very easily. The stone walls help with that. So do the roots, the echo, and the dark water. But cenotes are also modern environmental systems affected by modern decisions. A hotel, a farm, a road, a train line, a sewage problem, or a growing town can all become part of the story. The stone wells may look ancient, but they are not sealed away from the present. For a sleepy science journey, that might sound a little too practical, but practical things are often where the real wonder lives. The same opening that once gave a Maya community access to drinking water may now be visited by travellers from across the world. The same aquifer that filled a sacred well may now supply homes, hotels, and towns. The same underwater passages that preserve ancient bones may also reveal whether the water is healthy today. The old and the current are not separate here. They share the same limestone. And then there is the feeling of looking down. Many cenotes have a way of making people pause before entering. Even the cheerful ones. Even the popular ones with changing rooms and ticket booths. You walk toward the opening and the air changes slightly. The temperature drops. The sound of the outside world becomes softer or more echoing. You see the water below, sometimes bright, sometimes shadowed. If the cenote is open to the sky, you may see clouds reflected in the surface. If it is inside a cavern, you may see lamps or daylight catching the rock walls. The place seems to invite ordinary behaviour. Take off your shoes, step down, swim, float, laugh. But at the same time, something older is present. Not supernatural necessarily, just older. Stone, water, darkness, and a hole that leads into a system bigger than your body understands. That is the part scientists and divers learn to respect. The entrance is easy to admire. The underground system is not something to treat casually. A cenote may be the mouth of a cave. From that mouth, passages can extend beyond sight. The water may look perfectly still, but it may be moving slowly through fractures and tunnels. The bottom may be shallow near one edge and then drop sharply. There may be restrictions, silt, submerged formations, delicate archaeology, and fragile habitats. A swimmer sees a beautiful pool. A cave diver sees a set of conditions. An archaeologist sees context that must not be disturbed. A hydrologist sees access to the aquifer. A local resident may see a place tied to family, community, and memory. All of those views are true at the same time. This is why the cenotes are such a good entrance into the larger mystery of the Yucatan tunnels. They begin with something anyone can understand. A hole, water, stone, shade. Then, as soon as you ask one careful question, the simple picture opens. Why is the hole here? How deep is it? Does it connect to another one? Where did the water come from? How old is the cave? Who used it? What lies at the bottom? What moves through it at night? What changes when the rainy season comes? What happens when the sea level changes? What did this place look like before it flooded? Each question leads downward. The word well makes a cenote sound domestic, almost ordinary. We imagine a circle of stones and a bucket, something village-like, something manageable. But these wells are made by collapse, dissolution, and underground drainage. Some open into chambers big enough to make a person feel very small. Some lead into cave systems that require years of mapping. Some contain records of climates, extinctions, rituals, and migrations. A stone well in Yucatan can be a water source, a cave entrance, a shrine, a scientific archive, and a hazard all in the same afternoon. There is no need to exaggerate them. They are already unusual enough. Perhaps the most calming way to understand a cenote is to think of it as a meeting point. Rain meets rock, surface meets underground, fresh water meets salt water, somewhere deeper in the system. Human history meets geology. Daily life meets ritual. Light meets darkness. A person standing at the rim meets the fact that the ground is not always as solid as it looks. And if you listen to stories from divers who work in these places, or read accounts from researchers who study them, you notice a consistent theme. The entrance is never the whole story. The pool is only the visible part. Below it, the shape of the land continues in secret. The tunnels branch. The water moves. The cave remembers dry periods, flooded periods, animal visitors, human visitors, storms, collapses, and the slow chemistry of limestone giving way. So, as we move on from the open wells and begin following the water itself, keep that image in mind. A blue circle in the jungle, a stone wall descending into shade, the surface calm enough to reflect the sky. Beneath it, a passage opening into the dark, carrying rainwater through a peninsula where rivers often choose to travel underground. Factual grounding for this section: cenotes are natural sinkholes formed when limestone or carbonate rock collapses and exposes groundwater, and they have long served as major freshwater sources in much of the Yucatan. The peninsula's karst limestone allows rainwater to percolate rapidly into the aquifer, with fresh water often forming a lens above saltwater. Recent studies and reporting also describe the region's extensive cenote and cave systems, and their environmental vulnerability. From the rim of a cenote, the water may look still. A leaf lands on the surface and drifts slowly. A small fish moves near the edge. Sunlight slides down the wall and stops where the shadow begins. Everything seems quiet enough that you could believe the pool has been sitting there by itself, minding its own business, like a natural bowl left behind in the jungle. But beneath that quiet surface, Yucatan is not still at all. The peninsula is carrying water. Not in the obvious way a mountain valley carries a river, with white water, stones, banks, bridges, and people pointing at it from picnic blankets. Yucatan carries water mostly out of sight. Rain falls on the forest, on towns, on old roads, on ruins, on hotel roofs, on farms, and on the thin soils above the limestone. Then much of it slips downward. It does not gather into long surface rivers across much of the northern peninsula. It filters into cracks, joints, cavities, and channels. It enters the rock, joins the aquifer, and begins moving through the hidden spaces below. This is where the story of the cenotes becomes larger than the cenotes themselves. Each open pool is not just a destination. It is a point of access to a much wider underground water system. The pool is the part you can photograph. The rest continues beyond the frame. The easiest way to picture this is to imagine the Yucatan not as a flat piece of solid stone, but as a broad sponge made of limestone. That is not a perfect comparison, because limestone is still rock, and if you drop it on your foot it will not feel like a sponge in any helpful way. But as a landscape, it can behave a little like one. It has pores, cracks, tunnels, and chambers. Some are tiny, some are large enough for divers to swim through, some are connected, others are blocked, collapsed, or not yet explored. Water enters, collects, moves, mixes and drains, not through one neat pipe, but through a complicated underground network. This is one reason the phrase underground rivers is both useful and slightly misleading. In some places beneath Yucatan, water really does move through cave passages that feel river-like, especially to divers following a tunnel where the flow can be sensed. But much of the aquifer is not a single river with two banks. It is a system. Water moves through conduits, fractures, pores, and cave channels, sometimes slowly, sometimes more directly, depending on the rock and the route. It is less like one hidden Nile beneath the jungle, and more like an enormous underground plumbing system designed by rainwater, chemistry, gravity, sea level, and geological accidents. A plumber would probably ask for a new profession. Because the land is low and flat, gravity has only a gentle slope to work with. There are no towering mountains pushing rivers downhill in the usual dramatic way. The peninsula rises only modestly above sea level in many areas, especially near the coast. Yet water still moves. It tends to flow from inland areas toward the sea, following hydraulic gradients through the limestone. In places it emerges as coastal springs, submarine groundwater discharge, wetlands, lagoons, and hidden outlets along the shore. The journey may begin as rain falling on a patch of forest far inland and end as fresh water seeping into a coastal lagoon or mixing with the Caribbean below the surface. A person standing on a beach may see waves, sand, and tourists trying to keep towels from blowing away. Underneath, fresh groundwater may be pushing seaward through the rock. Salt water from the ocean pushes inland below it. The two waters meet underground. Because fresh water is less dense than salt water, it tends to float above the denser marine water, creating what scientists often call a freshwater lens. This lens can be thick in some parts of the peninsula and much thinner near the coast. It is not a hard object, of course. It is water arranged by density, pressure, recharge, tides, rainfall, and the shape of the aquifer. Still, the lens is real enough to matter. It is the main source of usable fresh water in much of the region. That fact gives the hidden rivers a very practical importance. The same underground system that fills cenotes also supplies water for people, towns, farms, hotels, forests, wetlands, and coastal ecosystems. This is not just a mysterious world for cave divers and scientists with waterproof notebooks. It is a working water source. Every rainfall, every dry spell, every new building, every waste system, and every decision made at the surface can become part of the story underground. Karst aquifers can be especially vulnerable because water can move through openings quickly. In some landscapes, layers of soil and sediment filter water slowly before it reaches the aquifer. In karst, that filtering can be limited. Cracks and conduits may allow water, and anything carried with it, to move faster than expected. That means pollution does not always stay politely near its source. Wastewater, fertilizers, chemicals, and other contaminants can enter the underground system and travel. The cenote that looks clear enough to drink from may still be connected to a route affected by activities far away. Clear water and clean water are not always the same thing, which is one of those facts that feels unfair but important. The hidden rivers also explain why cenotes are connected in ways that can surprise people. From the surface, two cenotes may appear separate, divided by forest, a road, or a village. Underwater, they may belong to the same system. A diver can enter one opening, follow a guideline through a passage, and eventually reach a different cenote entirely. To someone above ground, the two pools seem like separate places. To the water, they may be rooms in the same house. This is part of what has made Yucatan and nearby Quintana Roo so important for cave exploration. The flooded cave systems there are among the longest known underwater cave networks in the world. Their maps are made slowly and carefully by trained cave divers who measure passages, mark lines, document directions, and connect known systems when exploration proves that one tunnel leads into another. A map that once showed separate systems can change when a connection is found. Suddenly, two underground worlds become one larger world. The surface did not change. The understanding changed. There is something quietly humbling about that. The land can be walked, driven across, photographed, sold, fenced, and named, while the water below continues by routes that do not care much about surface boundaries. A town may sit above a passage, a forest may stand over a chamber, a road may cross a hidden conduit. People may live their lives above the aquifer without ever seeing the route that rainwater takes below them. Then one cenote opens, one diver follows one line, one scientific survey adds one more piece, and the hidden map grows. The water itself is not always uniform. In many cenotes and underwater caves near the coast, divers encounter a halocline, the zone where fresh water and salt water meet. It can look like a shimmering sheet or a blurry layer suspended in the water. Above it, the water is fresher. Below it, the water is saltier. Passing through it can make vision distort for a moment, as though someone has smeared the world with invisible oil. Lights blur, rock edges wobble. A diver's hand may look strangely bent. Then, below the layer, the water clears again, but it is a different water mass. This meeting of fresh and salt water is more than a visual oddity. It is part of the chemistry that shapes the caves. Where waters of different chemistry mix, they can become more aggressive at dissolving limestone. In coastal karst systems, this mixing corrosion can help enlarge cavities near certain depths. Over long spans of time, the meeting zone between fresh and salt water can become a place where the cave grows wider. The tunnel is not just a path water uses, it is partly made by the water's own chemical behaviour. That is a neat trick, although it takes so long that calling it a trick may be giving it too much energy. Rainfall changes the system too. During wet periods, more water enters from above. The freshwater lens may thicken or shift. Flow can increase through certain conduits. During dry periods, recharge decreases. Near the coast, tides can affect water levels in caves and cenotes. Storms and hurricanes can add sudden pulses of water, pressure, sediment, or organic material. The aquifer may look silent, but it is responding to weather all the time. Not loudly, not with the obvious rise of a riverbank after rain, more subtly through levels, chemistry, flow, salinity and pressure. This is one reason scientists study cenotes as monitoring points. A cenote gives access to water that would otherwise be hidden inside the rock. Researchers can measure temperature, salinity, dissolved oxygen, nutrients, contaminants, isotopes, and other chemical clues. They can use those measurements to understand where the water came from, how long it may have been underground, what rock it interacted with, and whether it is mixing with seawater. The cenote becomes a natural sampling window. It is a doorway not only for swimmers, but for data. That word data may sound less romantic than a blue pool beneath the trees, but there is something very satisfying about it. A scientist lowers an instrument into a cenote. The instrument records numbers. Those numbers reveal movement, mixing, pollution, recharge, or seasonal change. The hidden river becomes a little less hidden. Not because someone drained the cave or lit it up like a shopping centre, which would be a terrible idea, but because careful measurements make the invisible system legible. Yet the system remains difficult to understand fully. Karst is complicated by nature. Water does not move evenly through it like ink spreading through paper. It may move quickly through one conduit and slowly through surrounding rock. Two nearby locations can behave differently because one is connected to a major passage and the other is not. A contaminant may appear in one cenote and not in another nearby one. A rainfall pulse may reach one monitoring point quickly and another much later. The aquifer is not a smooth underground lake. It is a maze of different pathways. That complexity is part of why some routes still puzzle researchers. It is not that the basic science is unknown. Limestone dissolves, water flows, sea level changes, fresh and salt water mix, caves form. Those processes are understood. The challenge is detail. Which passage connects to which? How fast does water move through a specific route? Where does a particular flow emerge at the coast? How does development above ground change water quality below? How will sea level rise affect the freshwater lens? Which cenotes are most vulnerable? Which unknown passages carry important flow? The more specific the question becomes, the more the underground world resists easy answers. There is also a problem of access. In an ordinary river, researchers can walk along the bank, place gauges, sample water, map channels, and return in daylight with lunch. In an underwater cave, even reaching the study site may require specialized training, equipment, and risk management. A cave passage may be far from the entrance. Instruments must be carried in, secured, recovered, and maintained. Sediment can be disturbed. Visibility can change. Some passages are too narrow or fragile. Some areas may contain archaeological material that should not be touched. The water system is scientifically important, but it does not make itself convenient. The aquifer has no reception desk. Because of this, cave divers often play a key role in expanding knowledge. They are not simply thrill seekers swimming into dark holes, although the phrase dark hole does tend to attract a certain kind of personality. Properly trained exploration divers map passages, place survey markers, document features, help archaeologists locate sites, assist hydrologists, and sometimes collect samples. Their work can be slow and repetitive. Tie line, measure, note direction, check depth, watch gas, avoid silt, protect formations, turn the dive before it becomes unsafe, return, draw the map, then do it again. The romance of exploration includes a surprising amount of discipline. The hidden rivers also connect to life. Some cave systems contain animals adapted to darkness, including small crustaceans and fish that may have reduced eyes or no pigment. These creatures live in conditions very different from the sunny surface world. Energy may come from organic material washed in from above, microbial communities, bat guano in air-filled sections, or other subtle sources. The ecosystem is not lush like a coral reef. It is sparse, specialized, and vulnerable. A change in water chemistry, pollution, or sediment can matter a great deal. Near the coast, the aquifer interacts with mangroves, lagoons, wetlands, and marine environments. Fresh groundwater discharge can influence coastal water chemistry and ecosystems. Nutrients carried through the aquifer may feed some systems, but excess nutrients from human sources can cause problems. Again, the hidden rivers are not separate from the visible world. They are connected to it at many points. What happens underground can reach the sea. What happens at the coast can push back into the aquifer. This connectedness is one of the most important ideas to carry through the whole journey. A cenote is not just a pretty stop on a travel route. A tunnel is not just a dramatic place for divers. A cave pool is not isolated because it is quiet. The Yucatan aquifer is a shared system. The water moving below the jungle may pass through places no one has mapped, beneath land used by many different people, and eventually toward ecosystems that depend on the balance between fresh and salt water. It is all one conversation, conducted in limestone. Human history followed those hidden rivers too, even when people could not see them directly. Ancient settlements depended on reliable water. Travellers and communities knew the locations of cenotes. Some openings became central to towns. Some were used for ceremonies. Some were feared, respected, or protected. The underground water shaped where people could live, how they moved, how they understood the land, and how they related to the unseen. In a region where the most important water often came from below, the underworld was not an idea far away from daily life. It was underfoot. There is a practical kind of awe in that. People looked into a cenote and saw drinking water. They also saw depth. They knew the pool was part of something larger. Modern science changes the vocabulary, but not the basic fact. Today we may speak of karst hydrology, density stratification, aquifer vulnerability, hydraulic gradients and groundwater recharge. Older communities may have spoken through stories, rituals and place names. Both were responses to the same landscape. a land where water disappears and returns through stone. The hidden rivers can also change how we imagine the surface of Yucatan. A road through the jungle no longer feels like it rests only on dry rock. A field is not just a field. A town square is not just a square. Somewhere below, water may be moving. It may have fallen as rain weeks, months, or longer ago. It may be passing through a narrow fracture, filling a chamber, sliding above salt water, or heading toward a spring near the coast. It may pass close to bones from the Ice Age, roots from today's forest, and the foundation of a modern building, all without any of them knowing much about the others. This is where the underground tunnels become hard to explain in the ordinary sense, not because they break the laws of nature, but because they exceed the neat categories we like to use. A tunnel can be geological and archaeological. A river can be invisible and essential. A cenote can be a water source and a sacred place. A cave can be a habitat, a hazard, a climate archive, and a tourist attraction. The hidden river is not one thing. It is a moving link between many things. When scientists say more work is needed to understand the Yucatan aquifer, that does not mean nothing is known. It means the system is large, complex, and unevenly mapped. It means a measurement from one location cannot always explain another. It means underground conduits can create fast routes that surprise people. It means coastal saltwater intrusion, population growth, tourism, agriculture, wastewater, storms, and sea level rise all interact with a system whose details are still being discovered. The mystery is not a single locked box. It is a moving body of water beneath a changing landscape, and there is another layer to this. The hidden rivers of Yucatan are not only present-day water routes, they're also part of a long history of changing sea levels. During colder periods of Earth's past, when much more water was locked in ice sheets, global sea levels were lower. Parts of today's flooded cave systems were dry. Rainwater still dissolved limestone and formed caves, but the water table was lower. Passages that are now underwater could once be walked through by animals and humans. Later, as the climate warmed and ice melted, sea levels rose. The water table rose with it. The caves flooded. What had been air-filled became submerged. The hidden rivers changed their position in the rock. That means a diver swimming through a flooded tunnel today may be passing through a space that has had multiple lives. First a developing void in limestone, then a dry cave with dripping mineral formations, then a place visited by animals and sometimes by people, then a flooded passage in a modern aquifer. The tunnel is not only a route through space, it is a record of changing conditions through time. The walls, formations, sediments, bones and chemistry all belong to that record. It is easy to see why these places attract careful explorers. Every bend in a passage can hold information. A stalactite underwater tells you the cave was once dry, because such formations grow in air-filled spaces from dripping water. A layer of sediment may point to flooding or flow changes. Bones may reveal extinct animals or early human presence. Water chemistry may show mixing with seawater or contamination from the surface. A cave map may show patterns related to fractures, sea level, or the buried edge of an ancient crater. Nothing is just decoration down there. Even the quiet parts are doing work. For the listener drifting towards sleep, though, all this science can settle into one simple image. Rain falls on Yucatan at night. It lands on leaves and rooftops. It runs down trunks, slips through soil, and finds cracks in pale limestone. It moves away from the sound of insects and the warmth of the surface. It joins other water in the dark. Some of it rests in a cenote. Some of it moves through a passage. Some of it slides slowly toward the coast above denser salt water. Some of it passes through tunnels that humans have mapped, and some through spaces no one has entered. The surface world goes on. A dog barks, a scooter passes, someone closes a door. Underneath, the water continues, not quickly enough to be noticed in a single moment, but steadily enough to shape a peninsula. And as that water moves, it carries the next part of the story with it. Because the hidden rivers are not spread randomly through Yucatan. Some cenotes appear in patterns. Some lines and clusters seem to follow older structures in the rock. One of the most famous patterns is a broad arc across the northern peninsula, a ring of openings that helped scientists identify something buried below the surface. It points back not merely to ordinary cave formation, but to a much older event, an impact so large it changed Earth's history and left a scar now hidden under limestone, villages, forest and water. The rain falls gently, the cenotes wait. The underground rivers move through stone, and beneath the map of water there is another map, older and stranger, drawn by an asteroid before the caves were ever filled. The hidden rivers of Yucatan do not only follow the limestone, they also follow an old wound. At first that may sound too dramatic for a place now filled with forests, villages, roads, birds, hammocks, food stalls, quiet churches, and people going about ordinary afternoons. If you stand in northern Yucatan today, you do not see a crater. There is no gigantic smoking bowl in the ground. There are no black cliffs circling the horizon. There is no convenient sign saying, "Please mind the edge of the ancient asteroid scar." The land looks low, broad, and calm. In many places it looks almost stubbornly normal, as if it has no intention of explaining what happened to it. But buried beneath the limestone and younger sediments is the Chicxulub impact structure, one of the most famous impact sites on Earth. Around 66 million years ago, near the end of the Cretaceous period, a large asteroid struck the region that is now the northern Yucatan Peninsula and the Gulf of Mexico. The object was roughly the size of a city. When it hit, it released an amount of energy so enormous that the comparison to ordinary explosions quickly stops being helpful. It blasted rock, vapour, dust, and debris into the atmosphere. It triggered fire, shock waves, earthquakes, tsunamis, and global climate disruption. The impact is widely linked with the mass extinction that ended the age of non-avian dinosaurs and changed the path of life on Earth. That is the large version of the story. A cosmic object arrives, the planet changes, dinosaurs vanish except for the bird line. Mammals eventually get more room to diversify. Much later, one of those mammals invents sandals, sunscreen, and guided cenote tours. But the part that matters for our journey is not only the extinction, it is what the impact left behind in the rock. The Chicxulub crater is not exposed at the surface like some craters on the moon. It is buried. Scientists recognized it through geophysical evidence, drilling, gravity and magnetic data, shocked minerals, and the strange agreement between invisible structures underground and visible patterns above. One of those visible patterns is the Ring of Cenotes, a broad semicircular band of sinkholes in northwestern Yucatan. On a map, many cenotes appear arranged in a curve, not a perfect circle drawn with a compass, because geology does not usually care about satisfying human neatness, but close enough to raise a serious question. Why should natural wells appear in a ring? For a long time, cenotes were understood locally and regionally as water sources, cave entrances, and sacred places. But when geologists began looking at the broader pattern, the ring became a clue. The surface distribution of cenotes seemed to trace part of the buried crater structure. In other words, the holes in the limestone were marking something much older below them. The wells were not the crater itself, but they were related to weaknesses, permeability, fractures, and hydrogeological changes influenced by the impact structure. The land had healed over, but the water still knew where the damage was. That is a useful way to think about it. Rock remembers differently than people do. A person remembers with images, words and feelings. Rock remembers with fractures, density contrasts, mineral changes, buried layers, and zones where water can move more easily. The Chicxulub impact did not leave a visible rim that anyone could walk around with a packed lunch. Instead, it left a hidden structure. Later, as limestone formed, dissolved, cracked, compacted, and interacted with groundwater, certain zones became more favourable for cenotes and cave development. Water used the weaknesses. Dissolution widened them, collapse opened them. The result, seen from above, was a ring of openings in the stone. The diving cave's explanation of cenote formation describes this sequence in a simple way. The Yucatan limestone began as marine deposits in shallow seas, later forming thick carbonate bedrock. Then the Chicxulub impact fractured the region and created zones of weakness. Over millions of years, rainwater and groundwater dissolved the limestone, enlarging underground cavities and passages. In some places, the roofs collapsed, forming cenotes. It is not that the asteroid carved each cenote directly, like a cosmic drill making wells for future swimmers. That would be tidy but wrong. The impact helped create structural conditions. Water did the slow work afterward. The ring is a long collaboration between catastrophe and patience. This is one of the strangest things about Yucatan. A visitor can climb down wooden steps into clear water, hear someone laughing nearby, feel a few tiny fish brush past their feet, and be inside a landscape shaped partly by the same event that helped end the dinosaur era. The connection is not obvious in the moment. The water is cool, the stone is pale, the vines hang down. Someone is probably trying to take a photo without dropping their phone. Nothing about it feels like planetary disaster, and yet the arrangement of many cenotes across the region points back to that buried impact structure. The ring itself is often described as a semicircular belt across northern Yucatan. It arcs inland and roughly follows part of the crater margin. The crater continues offshore beneath the Gulf of Mexico, so what appears on land is only part of the whole structure. UNESCO's tentative list description for the Ring of Cenotes describes a broad belt several kilometers wide, with a semicircular form centered around the Chicxulub area, and notes its importance for the peninsula's geohydrology. The scientific article by Eugene Perry and colleagues, published in 1995, described a 180-kilometer diameter semicircular band of abundant karst sinkholes that coincides approximately with a concentric ring of the buried Chicxulub structure. That study also noted that the ring marks a zone of hypermobility, shown by the sinkholes themselves, coastal springs, breaks in coastal dunes, and water level patterns. Hypermobility is a quiet phrase, but it is doing a lot of work. It means water can pass through more easily. In a karst peninsula where groundwater is everything, a zone of high permeability is not just a geological curiosity. It shapes the way water moves, it influences flow paths, it affects where dissolution happens, where caves enlarge, where cenotes collapse open, and where fresh water may move toward the coast. The ring is not just a pattern of holes, it is part of the plumbing. This is where the ancient impact becomes directly connected to the hidden rivers. The asteroid struck in a moment, the crater formed in violence, but the consequences did not remain trapped in that moment. The buried structure influenced later geology and hydrology. Fractures, faults, slumping, differential compaction, buried crater margin structures, and permeability differences all became part of the underground system that water would later use. Rainwater does not care that a fracture began with an event 66 million years ago. If the route is easier, water follows it. A helpful image is an old cracked plate covered with layers of plaster. From above, the surface may look smooth, but if water seeps through the plaster, it will find the cracks underneath. It will follow them, widen them, stain them, and reveal them indirectly. The original break may be hidden, but its pattern still guides what happens later. Yucatan is not a plate, of course, and the Chicxulub impact was not a kitchen accident, although on the scale of planetary housekeeping it was a serious one. But the idea is close enough. Hidden structure can shape visible features. Scientists have discussed several possible mechanisms for the Ring of Cenotes. The 1995 study mentioned possibilities such as faulting, permeability associated with a buried reef complex, or collapse related to impact deposits and later dissolution. Other work has considered how impact-related structures and later sedimentary processes may have controlled groundwater movement and sinkhole development. This is important because it keeps the story honest. The phrase, "the asteroid made the ring," is useful as a first step, but it is not the whole explanation. The ring likely reflects a chain of causes: impact structure, later burial, rock properties, groundwater flow, dissolution, collapse, and ongoing karst processes. Science often becomes more interesting when the simple sentence is replaced by a longer one. Not less beautiful, just more accurate. The cenotes are not mysterious because no one has any explanation. They are mysterious because the explanation is layered. A single sinkhole may have a local collapse history. A cluster of sinkholes may reflect local groundwater conditions. A ring of sinkholes may reflect regional structure tied to an impact crater. The same feature can be explained at different scales. Up close, it is a collapsed cave roof. From above, it is part of a hydrological belt. From deep time, it is a mark left by an asteroid and then edited by water for millions of years. The Chicxulub impact itself is one of those events that can be hard to hold in the mind. The asteroid was not large compared with Earth, it was large compared with things humans usually meet. Something around 10 kilometers across is enough to be abstract, too large to imagine as a rock, too small to imagine as a planet. It entered Earth's story in a single collision, and the result was global. The impact blasted material into the atmosphere. Dust and aerosols altered sunlight. Food chains collapsed. Many species disappeared. The world after the impact was not the world before it, and yet the Ring of Cenotes reminds us that even enormous events can leave subtle surface traces. Not all evidence is spectacular. Sometimes the clue is water in holes. That may be one reason this story feels so strange. We expect a dinosaur-killing impact to announce itself. We expect drama. We expect the land to look obviously injured. Instead, much of the evidence is hidden under younger rock and sediment. The crater is read through instruments, drilling, maps, and patterns. The Ring of Cenotes is one of the rare ways the buried structure speaks at the surface. It does not speak loudly. It speaks through the placement of wells, the movement of groundwater, and the curved arrangement of sinkholes. It is an old impact translated into hydrology. For the ancient Maya, the cenotes were not understood in terms of asteroid impacts. There is no reason they would have known about a buried crater found with modern geophysical methods. But they knew the cenotes mattered. They knew the water was essential. They built, settled, travelled, worshipped, and made offerings in a landscape shaped by the underground roots of water. In a quiet way, human life in northern Yucatan was shaped by consequences of the impact long before anyone could name Chicxulub as an impact structure. The crater influenced the water influenced settlement influenced culture. A rock from space helped shape the ground beneath a civilization that would never know the rock existed. There is something almost funny about that, in a very large and serious way. Imagine trying to explain to someone drawing water from a cenote centuries ago that the reason so many wells lie along a curve may involve an asteroid older than humanity, older than the current forests, older than the caves as they look today, and connected to the extinction of animals they had never seen. It would be a difficult conversation. It might require diagrams. It might also require you to prove you are not simply someone who had spent too much time in the sun. Modern science can now draw those diagrams, though even modern diagrams remain incomplete. The crater is buried beneath about a kilometre of younger sediments in places. Its structure is inferred from gravity anomalies, seismic surveys, drilling, and geological samples. The cenote ring helps mark the approximate outline of part of it on land, but it is not a perfect exposed rim. It is a surface expression of deeper conditions. This distinction matters. A cenote is not a crater wall. A sinkhole is not a meteorite fragment. The water-filled openings are younger karst features that appear to be organised by older impact-related structures. That is more complicated, but it is also more interesting. The ring's relationship with groundwater is especially important. Perry and colleagues describe the ring as a zone where groundwater behaviour changes, including high permeability and water level patterns that suggest influence on regional flow. UNESCO's description also emphasizes the ring as part of the Yucatan watershed, affecting infiltration, recharge, filtration, and water movement toward the north. In a region where the aquifer supports a large population, this is not only an ancient story, it is present-day infrastructure, made by nature and modified by human activity, though nature did not leave an instruction manual. If the ring is a preferential pathway for water, then contaminants, nutrients, and changes in recharge can also become part of that pathway. This matters for communities, conservation, and public health. The same structure that creates beautiful cenotes and unusual ecosystems can also make the aquifer vulnerable. Water can move through openings faster than expected, and the karst system may not filter pollutants as thoroughly as people might hope. An ancient impact can therefore have a modern environmental afterlife. It is not causing pollution, of course. People do that quite well on their own, but the structure of the land can influence how pollution moves. This is one reason scientists continue studying the ring. They want to understand not just where cenotes are, but how water moves between them, how the aquifer behaves, how coastal springs connect to inland recharge, and how the buried crater structure affects permeability. The more people depend on the aquifer, the more important these details become. A beautiful mystery is nice. A beautiful mystery that also supplies water is something you should probably understand before putting too much concrete on top of it. Still, the ring remains visually quiet. Many people who visit cenotes may never realize they are swimming in part of a large regional pattern. A person descends into a single pool. The experience is local. Cool water, stone walls, perhaps a shaft of light. But on the map, that one pool joins hundreds of others, forming a curved trace across the peninsula. One cenote is intimate. The ring is planetary. The same place can be both. That shift in scale is one of the best parts of this story. You begin with a small act, looking down into water. Then you ask why the water is there. That leads to limestone. Limestone leads to karst. Karst leads to underground rivers. Underground rivers lead to regional permeability. Regional permeability leads to the ring of Cenotes. The ring leads to Chicxulub. Chicxulub leads to the end of the Cretaceous, the extinction of dinosaurs, and the reshaping of Earth's biosphere, all from a pool in the jungle, where someone nearby may still be asking whether the ladder is slippery. The Yucatan makes scale feel strange. Human time, archaeological time, cave time, and planetary time overlap. A tourist visits for an afternoon. A Maya offering may be centuries old. A human skeleton in a submerged cave may be thousands of years old. A stalactite may record changes across tens of thousands of years. The limestone may have formed from ancient marine life over millions of years. The impact occurred 66 million years ago. The water passing through the system today may be recent rain. Everything is stacked together, not in a museum case, but in the ground. The ring also reminds us that landscapes are not always explained by what we can see. Yucatan's surface gives clues, but the reason behind those clues lies underneath. In some places, the land looks flat because younger sediments have covered the old structure. The crater is not obvious because time has buried it, yet groundwater responds to hidden differences below. The result is a pattern that only becomes clear when many cenotes are mapped together. One sinkhole is a feature. Hundreds of sinkholes arranged in a curve become a message. A careful message, though. The science does not say every cenote in Yucatan was made by Chicxulub. Cenotes form through karst processes across the peninsula. Many factors control their location and shape. The ring is a special concentration and arrangement associated with the buried crater structure, but cenotes exist outside it too. This distinction matters because overstatement can make real science sound like a myth, and the real science is already good enough. The asteroid did not create every underwater tunnel. It influenced a regional structure that helped guide water and dissolution in particular areas. That is still extraordinary. It also means that when people speak of underwater tunnels, scientists still cannot fully explain. Part of the difficulty comes from layered causation. A cave passage may be shaped by sea level changes, freshwater flow, saltwater mixing, fractures, collapse, sediment, and older structures inherited from the impact. To explain a tunnel, you may need chemistry, hydrology, structural geology, paleoclimate, and a good map. It is a little like trying to explain a family argument by looking only at who spoke last. The final collapse matters, but so does everything that made the collapse possible. The Ring of Cenotes is one of the clearest reminders that the underground world is connected to events far beyond ordinary human scale. The water in a cenote may feel personal. It touches skin, it cools the body, it reflects a face. But the place exists because of a history that includes shallow seas, marine organisms, limestone formation, asteroid impact, burial, fracturing dissolution, groundwater flow, sea level change and collapse. A swimmer meets the end result, not the whole process. Science tries to reconstruct the process without ruining the swim. There is also a kind of calm in realizing how slowly the later stages happened. The impact itself was sudden beyond imagining, but the cenote ring, as we see it through modern cast, belongs to long processes after the violence. Water seeped, rock dissolved, passages widened, roofs failed, openings appeared, life returned after extinction, forests grew, humans arrived, settlements formed, ceremonies took place, maps were drawn, divers entered, instruments measured. The planet absorbed catastrophe and turned part of it into a landscape of wells. That does not make the catastrophe gentle. It was not. But it shows how Earth reworks even violent events into later systems. The crater became buried. The buried structure influenced water. The water made caves. The caves became archives. The openings became sacred sites and water sources. The same event that ended many forms of life eventually helped shape places that sustained later life. Earth is not sentimental about this. It simply keeps working. If you imagine the ring at night from far above, with each cenote glowing faintly like a small blue point, the pattern becomes easier to feel. Not a perfect necklace, but a loose arc. Some points are famous, some are unnamed to outsiders, some are open pools, some are cave entrances, some are hidden by vegetation. Below them, groundwater moves through permeable zones. Deeper still, the buried crater structure rests under sediment and limestone, invisible but influential. The sky above is clear. The old impact came from that sky. The water below now reflects it. That is not a poem. It is just a very strange set of facts arranged in a way that makes the world feel larger. And as we leave the ring for now, the story begins to narrow again from the scale of an asteroid to the scale of a diver's light. Because some of the most remarkable places in Yucatan are not simply isolated cenotes on the ring, but long underwater cave systems where individual passages connect into networks of astonishing length. If the Ring of Cenotes shows us the hidden outline of a planetary scar, the cave systems show us what water can do when it is given weakness, limestone, time and darkness. They are not straight tunnels. They are branching routes, flooded rooms, restrictions, chambers and lines disappearing into black water. Somewhere beyond the open wells and the ancient impact pattern, a diver enters a passage, ties into a guideline, checks the light, watches the silt and moves forward. The surface is left behind. The crater is far below the level of thought. What remains is the cave itself, the next bend, and the long underwater labyrinth called Sakakton. The passage ahead does not begin like a grand entrance. There is no wide stone doorway, no carved arch, no sign from the ancient world saying, "This way to one of the largest flooded cave systems on Earth." It begins the way many Yucatan mysteries begin, with a cenote, clear water, limestone edges, and a surface that looks far too calm for what lies behind it. Near Tulum, in Quintana Roo, Under the forest and not far from roads, beaches, hotels and ruins, there is a cave system called Sac Actun. The name is often translated from Maya as White Cave, which feels appropriate when you see photographs from inside it. The rock can appear pale and smooth in the beams of divers' lights. The water can be so clear that stone formations look close enough to touch, even when they are farther away than the eye first guesses. Passages open into rooms, rooms narrow into tunnels, tunnels turn, split and continue. The cave does not behave like a single hallway. It behaves like a thought that keeps changing direction. For years, Sac Actun was known as one of the great underwater cave systems of the Yucatan. Nearby, another famous system, Dos Ojos, had its own reputation. Dos Ojos means two eyes, a name that comes from two neighbouring cenotes that look like paired openings into the same hidden world. To visitors, they could feel like separate places. To divers and mapmakers, the question was harder. Were they truly separate systems, or were they divided only because no one had yet found the right connection? That is one of the difficult things about underwater caves. On land, if two paths connect, you can usually walk around, look, climb, turn back, try again, and perhaps complain about your shoes. Underwater, especially inside a flooded cave, every search is limited by air, light, distance, visibility, equipment, training, and the need to come home by the same route. You do not simply wander. Wandering is for parks, shopping streets, and people trying to remember where they parked. In a cave, wandering is not a strategy. It is a warning sign. So the search for a connection between Sac Actun and Dos Ojos was slow. It required years of exploration and mapping. Divers had to follow known passages, push beyond familiar sections, test leads, survey new tunnels, and compare the growing maps. A lead is a possible continuation, a place where the cave seems to go farther. Sometimes it rewards the diver with a new passage. Sometimes it pinches down into rock, silt, or a place too tight to continue safely. Sometimes it looks promising, then ends in a blank wall, which is the cave's polite way of saying, "No, not here." In 2018, National Geographic reported that divers working with the Great Maya Aquifer project had found the connection. Sac Actun and Dos Ojos, previously treated as two enormous flooded cave systems, were shown to be connected. Under caving rules, when two systems are connected, the larger system absorbs the smaller name. So Dos Ojos became part of Sac Actun. At the time of the announcement, the combined system measured about 215 miles, or roughly 347 kilometres, and was described as the world's largest known flooded cave system. That record language can change as exploration continues, because cave systems do not politely stop expanding just because humans have printed a list. But the discovery remains extraordinary. Two giant underground worlds turned out to be one. Imagine that moment from the point of view of a map. For years, lines have been growing in different areas. Sac Actun here, Dos Ojos there. Each one measured, named, surveyed, respected. Then one small passage, one connection, one confirmed route changes the whole shape of the known system. What looked like two large structures becomes a single larger labyrinth. The surface stays the same, the roads stay where they are, the trees keep growing, the cenotes still look like separate openings, but underground the known world has changed. This is why Sac Actun is not only a cave, it is a lesson in how incomplete our sense of place can be. Above ground, we organise land by towns, fences, roads, property lines, paths and familiar names. Below ground, water follows limestone. It ignores the map on the wall. It moves through old passages and narrow cracks. It links places that may look unrelated from the surface. A cenote where people swim and another cenote several kilometres away may be part of the same flooded body. The distance between them, from the water's point of view, is not the distance along the road. It is the distance through stone. The scale of Sac Actun is hard to picture. because most people do not have a comfortable mental shelf for hundreds of kilometres of underwater cave. If someone says a road is 347 kilometres long, you may picture a long drive. Perhaps snacks, fuel stops, and one person in the car insisting the playlist needs more variety. But an underwater cave system is not a road. It is not straight. It does not have shoulders, exits, signs, or convenient rest areas. Its length is the measured length of branching passages, like adding together the roots of a complicated root system. A diver does not swim from one end to the other as though travelling a highway. Exploration happens in pieces, from entrances, along lines, through connected regions, with careful planning. The cave's layout is divided into areas that had their own histories of exploration. The Saskatoon region, Nohochna-Chich, Actun Hu, and Dos Ojos have all been described as parts of the larger system. Some areas are shallow and decorated with formations, some contain deeper pits, some lead toward coastal springs, some passages are low and silty, some are wide enough to feel open, at least by cave standards, which is not quite the same thing as open by normal human standards. In a cave, a passage can be called comfortable even if most people would describe it as a stone tube with emotional consequences. A trained cave diver moving through Saskatoon must treat every part of the system with caution. The water may be clear, but clarity does not remove danger. In fact, clarity can make the place feel deceptively gentle. You can see the walls, you can see the formations, you can see the guideline fading ahead. But the ceiling remains overhead. The exit may be far behind. If silt rises, visibility can vanish. If a light fails, darkness becomes complete. If a diver loses the line, the cave becomes confusing very quickly. Cave diving is built around preventing small mistakes from becoming final mistakes. That is part of what makes the mapping work so impressive. To a viewer, an underwater cave photograph may look peaceful. A diver floats in blue water, light beams reaching into a passage, stone shapes glowing softly. But behind that image is discipline. Lines are placed, distances are measured, compass bearings are taken, depths are recorded, notes are made, equipment is checked repeatedly. A new passage is not simply enjoyed, it is documented. It must become part of a map that other trained people can understand. Saskatoon grew through this kind of work, not through a single heroic swim, but through years of accumulated effort. One team finds a passage, another maps a connection, a lead is followed, a chamber is added, a nearby cave is explored, a gap narrows, a possible route is checked again. The map becomes longer, then more complex, then longer again. Exploration is often less like opening a treasure chest and more like doing a very serious puzzle while underwater, in the dark, with a limited gas supply. It is not the most relaxing hobby ever invented, though it has certainly given us some remarkable knowledge. The Great Maya Aquifer Project, often called GAM, brought together cave divers, archaeologists, scientists and researchers to study these flooded systems as part of a much larger aquifer. The 2018 Saskatoon and Dos Ojos connection was not only a sporting achievement or a record announcement. It mattered because the cave is part of a freshwater reserve, a biodiversity system, and an archaeological landscape. National Geographic reported that researchers described the system as containing many archaeological contexts, including evidence connected with early settlers of the Americas, extinct animals, and Maya culture. That means the cave is not just long, it is full of information. Length attracts attention because humans like records. Longest, deepest, oldest, largest. These words are easy to understand and easy to put in a headline. But with Saskatoon, the length is only one doorway into its importance. The system also preserves evidence from times when some passages were dry. It preserves bones of animals that lived in a different Yucatan, one with lower sea levels and dry cave entrances. It contains traces of human activity. It records changes in water, climate, geology, and sea level. Its passages are part of the aquifer that still matters to people living above it. It is not merely big, it is useful to science in many directions at once. That is why calling it a labyrinth is not just dramatic language. A labyrinth is not only a place where someone can get lost, it is a structure that forces slow movement, careful choices and attention to the path. Sac-Acton does exactly that. It resists quick understanding. You cannot explain it by pointing to one entrance. You cannot understand it from one swim, one dive, one map, or one photograph. It is a network, and networks require patience. Inside such a system, the cave may change character from one area to another. In some sections, divers report broad, decorated passages with stalactites and stalagmites, reminders that those parts of the cave were once air-filled. These formations grow when mineral-rich water drips through air, leaving calcite behind slowly over time. If they are now underwater, that tells you the cave's history changed. The passage was once dry enough for formations to grow. Later, sea level rose, groundwater rose, and the cave flooded. A diver moving past underwater stalactites is swimming through a former dry cave. That single fact makes the place feel strangely displaced, as if a room from one world has been moved into another. Other parts of the system are not so graceful. Some passages can be low, narrow, or unstable. Some may contain breakdown blocks where ceiling material has fallen. Some areas have poor visibility. Some are affected by flow. Scientific papers have described Sac-Acton as an anchialine cave system, meaning it is coastal and contains waters influenced by the connection between fresh groundwater and the sea. The system drains through coastal springs toward the Caribbean, so while the cave may look motionless in photographs, it is part of an active hydrological system. Water is moving through it, sometimes in ways divers can feel directly. That movement matters for the cave's shape. It also matters for the people above. The same conduits that drain the aquifer can carry contamination. Thin soils, fast groundwater flow, tourism development, wastewater, landfills, agriculture, and construction can all affect the system. Sac-Acton may look remote in photographs, but parts of it lie under a region where development has grown rapidly. The cave is not sealed away, it is connected, and connection is both its wonder and its vulnerability. This is the theme that keeps returning in Yucatan. The hidden world is not separate from the visible one. The flooded cave does not care whether a pollutant came from a luxury resort, a rural home, a road, or a careless visitor. Water carries what it carries. In a karst aquifer, it may carry it quickly. Protection, therefore, cannot be only about keeping one cenote pretty for tourists. It has to be about understanding the entire drainage system. A cave map becomes an environmental tool. A diver's survey line becomes part of water protection. Hydrology, archaeology, tourism, and public health are tied together in the same passages. There is a quiet irony in the fact that many people first meet Sac-Acton through beauty. Clear water, pale rock, blue light, calm photographs. The beauty is real, but it is not the whole truth. The system is also dangerous, fragile, scientifically dense, and difficult to manage. It contains ancient evidence and modern risk. It is a place where one careless action can damage formations that took thousands of years to grow, stir sediment around remains, or disturb a habitat that evolved in darkness. The cave is generous with wonder, but not forgiving of carelessness. The archaeological side of Sac-Acton adds another layer of seriousness. National Geographic reported that researchers found more than 100 archaeological contexts in the larger system, including remains of extinct animals, human evidence, ceramics, and Maya material. Some finds belong to periods when the cave was dry or partly dry. Others relate to later Maya use of cenotes and caves. A submerged cave can preserve material well, because water may protect objects from some forms of disturbance, but it also makes study difficult. Researchers must document finds in place, avoid disturbing context, and interpret them with attention to geology and water history. Context is everything in archaeology. A bone by itself can tell you something. A bone's position, surrounding sediment, mineral coating, depth, associated objects, and location inside the cave can tell you much more. Remove it without care and part of the story disappears. This is why trained scientific work matters so much in underwater cave archaeology. The cave is not a cabinet of curiosities, it is an archive, and the archive is written in placement. Some of the most famous discoveries in the broader Sakakton system include ancient human remains and Ice Age animal remains, especially in areas such as Hoyo Negro, a deep pit in the Aktunhu region. Hoyo Negro is often discussed because of the remains of Naya, a young woman whose skeleton provided important evidence about early people in the Americas. That story deserves its own careful space later, because it connects to bones, migration, sea level, and the question of how humans used caves when they were dry. For now, it is enough to know that Sakakton is not only a cave map, it is a place where the past stayed behind in the dark. The no easy ending in this labyrinth comes from the fact that every discovery seems to open another question. When Sakakton and Dos Ojos were connected, the map did not become complete. It became larger. The connection did not say, "Now we know everything." It said, "These two things were one thing, and there may be more." Scientific papers before the 2018 announcement already noted that other cave systems in the region had potential to connect with the main system. Exploration continues because the limestone continues beyond the last surveyed line. In cave work, the end of the map is not always the end of the cave. Sometimes it is only the place where the last safe survey stopped. This is the part that makes Sakakton feel alive as a scientific subject. It is not finished. Its ranking among the world's longest underwater cave systems can shift as other systems are mapped and extended. Its known length can change. Its environmental condition can change. New archaeological context can be documented. New hydrological measurements can refine understanding of flow. A cave that took enormous time to form is still changing in human knowledge from year to year. For a viewer drifting through this story at night, the important thing is not the exact current ranking on a list, though the numbers are impressive. The important thing is the mental image of a hidden structure so large that the surface gives almost no hint of it. Think of a normal day in Tulum. People eat breakfast, traffic moves, shops open, tourists walk toward beaches, workers repair roads, birds cross above the trees, and below all of that, a flooded labyrinth stretches through limestone linking cenotes, carrying water, preserving remains, and waiting beyond the reach of ordinary sight. It is easy to imagine the first few meters of a cave dive. The diver descends through a cenote. Daylight still reaches the entrance. The water is clear. The guideline begins. The beam of the light touches pale stone. The entrance behind remains visible for a while, a blue window back to the ordinary world. Then the passage turns. The blue window fades. The cave becomes the whole environment. There is no sky now, no trees, no breeze, only water, rock, bubbles, line, light, and the steady awareness that the way forward must always include the way back. This is why Sakakton deserves respect, not just fascination. The cave is not a movie set. It is not a haunted attraction. It is not a place where mystery means fantasy. Its real mystery is harder and better. How do all these passages connect? How did each section form? Which routes carry the most water? What remains inside still has not been documented. Which areas are most threatened by pollution or development? How can people protect a system they cannot fully see? Those questions are not solved by one discovery. They require mapping, monitoring, training, regulation, and patience. Sakakton also changes the way we think about the word underground. Usually underground means beneath us, and beneath us feels less important than what is around us. Out of sight becomes out of mind. But in Yucatan, underground is where the water is. Underground is where the caves are. Underground is where some of the oldest evidence is preserved. Underground is where fresh and salt water meet. Underground is where the future of the aquifer may be decided by choices made above. The hidden world is not below the real world. It is part of it. And perhaps that is the quietest lesson of the labyrinth. A place does not need to be visible to be central. The tunnels of Sakakton do not announce themselves from the road. They do not appear on the horizon. They do not cast shadows at sunset. Yet they shape water, hold history, and challenge scientists to keep looking. One confirmed connection turned two famous systems into one. Another future connection may change the map again. Somewhere past the known routes, another passage may be waiting behind a restriction, below a halocline, or beyond a chamber where the line has not yet been pushed farther. For now, the diver's light moves across pale limestone. It catches a formation that grew in air long before the passage flooded. It catches the guideline, thin and practical, leading through the dark. It catches the slight shimmer of water ahead, where the cave's clarity begins to change. Because inside these systems, the water is not always one water. Fresh water and salt water can lie in layers. Between them is a strange boundary that bends the view and makes the passage look briefly unreal, not because anything magical is happening, but because physics can be quite strange enough when left alone in a cave. The labyrinth continues, and the next thing waiting in it is not a wall, but a wavering line in the water, the halocline, where two kinds of water meet and refuse for a while to become one. The passage continues, and at first it still looks like one kind of water. That is the trick. Inside many cenotes and flooded caves of the Yucatan, the water can be so clear that it does not seem to be water at all. A diver may look ahead and see pale limestone, long formations, the thin guideline, and the soft beam of a lamp reaching farther into the cave. Everything appears sharp. The floor is visible. The ceiling is visible. A hand in front of the mask looks close and steady. The cave seems almost suspended in air, except for the bubbles, the gear, and the small practical reminder that breathing is currently being handled by equipment. Then the passage ahead begins to shimmer. At first, it might look like heat rising from a road on a summer day, which is a strange thing to see underwater. The edges of the rock seem to tremble. The beam of the light becomes less clean. The line ahead bends slightly, not because the line is moving, but because the water is bending the view. A diver reaches the layer, passes through it, and the world blurs. For a few seconds, everything becomes soft and doubled. The stone wall loses its outline. A hand can look stretched or broken. Another diver's fins may appear to melt into the cave. Then, a little deeper, the view clears again. This is the halocline. A halocline is a layer where the saltiness of the water changes sharply over a short distance. In the Yucatan caves, it often marks the meeting zone between fresher groundwater above and saltier groundwater below. The fresh water comes mostly from rain. It falls on the peninsula, slips through the limestone and gathers in the aquifer. The salt water comes from the sea, pushing inland through the coastal aquifer below the fresher water. Because fresh water is less dense than salt water, it tends to float above it. Salt water, being denser, settles below. Where they meet, there is not always an immediate smooth mixing. Instead, there can be a boundary, a transition layer, a visible shift in the water column. This is why the phrase, "where two waters refuse to mix," feels so accurate. Even though the waters do mix slowly and under the right conditions, they are not refusing in a human sense, of course. Water has no opinions, not even about people who enter caves with very expensive flashlights. But the difference in density allows the layers to remain distinct enough that a diver can see the boundary. Fresh water above, salt water below. Between them, a wavering zone where light behaves badly for a while. The visual distortion happens because the two water masses have different densities and different refractive properties. Refraction is the bending of light as it passes from one medium into another. You've seen it before in a glass of water when a straw seems to bend at the surface. The straw is not actually broken. Light is changing direction as it moves between air and water. In a cenote halocline, light passes through layers of water with different salinity and density. The result is not one clean bend, but a shifting blur. The world looks smeared, not because the cave is changing, but because the path of light is. It is one of those effects that sounds simple once explained and still feels strange when seen. A cave wall that was sharp a moment ago becomes soft. A diver's light scatters differently. The guideline looks as though it is waving in a current, even when the line itself is still. It can be beautiful. It can also be inconvenient, especially if you are trying to read the cave clearly. For trained divers, passing through a halocline is not only a visual experience, it is a condition to manage. The blur can reduce visibility. Movement can stir the layers together and make the distortion worse. In some places, a diver may choose to stay above or below the layer when possible, because swimming directly along it can be like trying to navigate through clear soup with a strong dislike for outlines. Near the coast, the halocline may appear relatively shallow. Farther inland, it is often deeper because the freshwater lens can be thicker away from direct seawater influence. The exact depth depends on many things: distance from the coast, rainfall, recharge, cave connectivity, permeability of the limestone, tides, storms, and the shape of the underground system. It is not a painted line on the wall. It moves. It changes. It may rise, sink, thicken, thin, or become more mixed depending on conditions. The cave may look timeless, but the water column is active. This is important because the halocline is not only something divers notice. It tells scientists how the aquifer is arranged. In coastal karst aquifers like Yucatan's, fresh groundwater forms a lens over saltier water intruding from the sea. That lens is precious because it is the usable freshwater supply. If too much fresh water is pumped out, or if sea level rises, or if recharge patterns shift, the saltwater interface can change. Saltier water can move upward or inland. Wells may become more saline. Ecosystems can be affected. The shimmering layer in a cenote is therefore not just a pretty underwater illusion. It is a visible sign of the balance between rainfall, groundwater, and the sea. A person floating at the surface may never notice it. The water above can feel fresh and clear. Someone swimming with a mask in a tourist cenote may see fish, roots, stones, and the glow of sunlight, but never go deep enough to reach the halocline. A cave diver descending farther may cross into a different water mass entirely. That is another reminder that a cenote is layered in more than one way. There is the surface experience, bright and simple. There is the cave experience, enclosed and careful. And there is the hydrological experience, where the water itself has structure. In some cenotes, the halocline can sit like a ghostly floor inside the water. From above, a diver may look down and see the lower layer shimmering. It can look almost like another surface beneath the surface, a second skin of the cenote. In the famous deep cenote known as the pit, divers often describe layers of water, light, and hydrogen sulfide clouds, though each site has its own conditions. In other caves, the halocline is less theatrical but still noticeable, a blurred zone at a certain depth. It may not announce itself until the light hits it at the right angle, and then suddenly the entire passage seems to ripple. The reason these layers exist goes back to the peninsula's shape and geology. Yucatan is a low limestone platform surrounded by sea. Rainwater enters from above. Seawater can intrude from the coast below. The rock is full of openings. The result is a density stratified aquifer, meaning water is arranged in layers according to density. Fresh or brackish water lies above more saline water. The halocline is the transition between them. This arrangement has been studied in many scientific ways. Researchers measure salinity profiles, temperature, dissolved oxygen, nutrients, methane, flow, and chemical changes across the water column. They lower instruments into cenotes. They place sensors in caves. They study how tides and storms move the interface. Recent hydroacoustic research in Yucatan flooded caves has looked at how oceanic and atmospheric events help drive mixing between the meteoric lens, which means fresh or brackish water from rainfall and saline groundwater below. In simple terms, the boundary is not frozen. Weather and the ocean can push on it. The aquifer responds. That makes sense if you think of the system as connected rather than sealed. A cave is not a glass tank sitting underground. It is linked to rain above, sea at the edges, rock around it, pressure changes, and underground flow paths. When heavy rain falls, more fresh water can enter the system. When tides shift, pressure changes can move water in coastal conduits. When storms pass, oxygen and mixing patterns can change. A halocline may look like a quiet line, but it is part of a moving conversation. This is also where cave formation becomes especially interesting. In coastal limestone systems, the mixing zone between fresh and salt water can increase dissolution of the rock. Fresh water has one chemistry, salt water has another. When they mix, the resulting water can be more capable of dissolving limestone under certain conditions. Over long periods, that can help widen passages near the halocline. Some cave divers and geologists have observed that passages may be enlarged near or just above these mixing zones, suggesting that the halocline is not merely occupying the cave, it may have helped shape it. So the halocline is both a boundary and a tool. It separates water layers, and it can also help create the spaces those layers occupy. It is part of the cave's present and part of its past. The shimmering band a diver sees today may be close to a level where limestone has been dissolving for a very long time. The blur in the water is not just a visual effect, it is a clue to the cave's growth. This gives the Yucatan tunnels another layer of explanation. If you ask why a flooded passage is wide at one depth and narrower above or below, the answer may involve the position of past or present mixing zones. If you ask why caves developed in certain patterns, the answer may involve groundwater flow, fractures, sea level, and the chemistry of fresh and saltwater meeting. If you ask why the caves are still changing, the answer may include the same processes. Limestone does not stop reacting just because a human has drawn a map. A halocline can also be a biological boundary. Different water layers can hold different amounts of oxygen, nutrients, and dissolved chemicals. Some cave ecosystems are arranged around these chemical gradients. Microbes may thrive at certain interfaces where they can use available compounds. Small cave animals may occupy particular zones. In some flooded karst systems, microbial activity around redox boundaries, where chemical conditions change, can be important. To the casual eye, the cave may look empty. To a microbiologist, it may be a layered habitat with very specific neighbourhoods, though admittedly neighbourhoods without coffee shops. The darkness adds to the strangeness. On the surface, ecosystems often begin with sunlight. Plants photosynthesize. Food webs build from there. In caves, especially beyond the daylight zone, sunlight is absent. Life has to rely on other sources of energy. Organic material washed in from the surface, bat guano in air-filled areas, dissolved compounds, microbial processes, and connections to the outside water system. A chemical boundary like the halocline can become important because it is a place where different waters bring different ingredients together. Where ingredients meet, life sometimes finds a way to make a living. For divers, though, the first experience is usually visual. The halocline changes what seeing means. Above it, the cave may appear clean and sharp. Inside it, the cave becomes uncertain. Below it, the scene may clear again, but the water feels different. Salt water has slightly different buoyancy. A diver may notice the body and equipment responding subtly. The temperature may change too, depending on the site. None of this is dramatic in the way a storm is dramatic. It is a quiet shift. The cave does not shout. It adjusts the rules. Imagine moving slowly through a passage. The ceiling is low but manageable. The guideline runs ahead. The light reveals small ripples in the limestone. You approach the halocline. The line begins to shimmer. The cave wall loses its edge. Another diver passes through ahead of you, and their fin kicks mix the layers. For a moment, visibility becomes a milky blur. You slow down. You avoid stirring sediment. You keep close attention to the line. Then you pass into the lower layer, and the world sharpens again. It is still the same cave, but the water has changed. There is something oddly useful in that experience. It reminds you that clarity is conditional. The cave was never as simple as it looked. The water was not one thing. The view depended on staying within one layer. Cross the boundary, and the whole scene changes. This is not abstract. It is practical. It is physics touching the mask. The halocline also helps explain why some underwater videos of cenote diving look unreal. A camera passes through a shimmering layer, and the image wobbles. Light beams spread in strange ways. Divers appear to hover between two worlds. Viewers may assume a filter has been added, but often the cave is doing that itself. The footage is not necessarily edited to look dreamlike. The lens is filming what different densities of water do to light. This can be one reason cenote diving attracts people from all over the world. It offers clear water, dramatic limestone formations, shafts of light, and this rare chance to pass through a visible boundary between water masses. But it is worth saying again, gently but clearly, that seeing a halocline inside an overhead cave environment is not something untrained people should attempt on their own. Cenote cavern tours for certified divers stay within specific limits and are guided by professionals. Full cave diving requires specialised training. The beauty of the halocline does not reduce the seriousness of the place. The cave remains a cave. The ceiling remains overhead. The way out remains something you must know. For scientists, the halocline is also a warning line. It marks the relationship between fresh water and the sea. In coastal communities, that relationship can become fragile. If groundwater extraction increases, the fresh lens can thin, or the saline interface can shift. If development adds contamination, the freshwater system can degrade. If sea level rises, saltwater intrusion can become a larger concern. If storms become more intense, mixing patterns can change. A shimmering layer in a cenote may be beautiful, but it is also evidence of a balance that can be disturbed. Yucatan's freshwater lens is not unlimited. It is recharged by rain, and it floats over saline water. In some areas, scientific reviews describe groundwater use as restricted to a relatively thin freshwater lens. That matters for every community, farm and visitor relying on the aquifer. The cenotes reveal the water, but they do not create more of it. They are windows into a resource that must be protected. The halocline makes that resource visible in a way few things can. Usually when people talk about groundwater, it sounds invisible and technical. Aquifers are beneath us. Water tables are measured. Salinity is sampled. Reports are written. The public hears the terms and understands they are important, but the reality remains hard to picture. In a cenote, the halocline gives the aquifer a visible boundary. You can see where fresh water gives way to saltier water. You can see the thickness of the fresh layer, at least in that place. You can see the sea's influence beneath the jungle. That may be one of the most powerful things about these caves. They turn hidden systems into experience. You do not merely read that fresh water is less dense than salt water. You descend through the water column and watch the world blur at the meeting point. You do not merely hear that the peninsula is connected to the sea underground. You cross into saline water while still deep inside limestone below the forest. You do not merely learn that water chemistry shapes caves. You see the enlarged passage, the layered water, and the evidence of dissolution around you. And yet the halocline also hides as much as it reveals. It shows that two waters meet, but not exactly where all the water came from. It shows a boundary, but not every flow path. It reveals mixing, but not the full history of the cave. Scientists still need instruments, samples, models, maps, and repeated measurements. A diver's eye can notice the shimmer, but the aquifer's behaviour requires patient study. Even the word halocline can make the phenomenon sound more fixed than it is. Halo comes from salt. Cline refers to a gradient or slope. It is not truly a wall. It is a zone of rapid change. In some places, the transition can be sharp. In others, it can be thicker and more mixed. During or after strong weather events, the shape of the halocline can change. In connected cave systems, flow may stretch, fold, or disturb the boundary. Sometimes there can be more than one chemical transition, including shallow changes between fresh and brackish water and deeper transitions into more saline groundwater. The cave is layered, but the layers are alive to conditions. This is why a single dive, or a single sample, is not enough to understand the whole system. A halocline observed today may not sit at exactly the same depth next season. A cenote near the coast may behave differently from one farther inland. A cave passage with strong connectivity may respond differently from a more isolated chamber. The aquifer is not a set of neatly stacked liquids in a laboratory jar. It is a living groundwater system, though not living in the biological sense. It shifts under pressure, rain, tides, and time. For the listener, perhaps lying still now, the science can settle into a simple picture. Above, the jungle receives rain. The water seeps down and becomes part of the fresh lens. At the edge of the peninsula, the sea presses inward underground. The fresh water floats over the salt. Between them is a moving boundary, sometimes visible to those who descend far enough. Light enters that boundary and bends. The cave blurs. Then the water clears again. Nothing supernatural has happened. The world has simply shown one of its quieter mechanisms, and there is a peaceful honesty in that. The halocline does not pretend the cenote is one thing. It reveals the mixture. It shows that the water below Yucatan belongs both to rain and to sea. It shows that the cave is shaped by land and ocean together. It shows that what looks still may be layered, and what looks empty may be full of chemistry, motion, and life. As the diver moves beyond the shimmering zone, the passage continues. The light steadies. The line appears clear again. The limestone walls return to their sharp edges. But now the cave feels different. Not because the rock has changed, but because we know more about the water around it. We have crossed a boundary that explains something about the aquifer, something about the cave's formation, and something about its vulnerability. Ahead, the tunnel does not only hold water, it holds traces, objects that did not dissolve, bones that settled where they fell, remains from animals that entered when the cave was dry, human evidence from a time before the passages flooded, offerings placed into water by people who understood cenotes in a way both practical and sacred. The halocline tells us how two waters meet. The next quiet evidence tells us how time itself can gather below the surface and stay there, waiting in the dark. The water clears again after the halocline, and the cave begins to feel still in a different way. Not empty, not silent in the simple sense. A diver still hears breathing, bubbles, equipment, the soft movement of water around the body, but the cave itself does not move for the visitor. It waits. The limestone walls hold their shape. The guideline continues ahead. The beam of a light falls across stone, then sediment, then a pale shape on the floor that at first may look like another piece of rock. Then the eye understands. A bone. That is when the flooded caves of Yucatan stop being only tunnels. They become archives. Not archives with shelves, labels, climate control, and a person at the front desk asking you not to bring in coffee. These are archives made of water, darkness, limestone, sediment, and accident. They do not organize themselves for easy reading. They preserve things without explaining them. A fossil may lie near a mineral formation. A human bone may rest in a chamber that is now reachable only by trained cave divers. A pottery fragment may sit in silt. A wooden object may survive because the conditions below the surface protected it from the ordinary damage of air, weather, animals, roots, and people. The cave keeps things, but it does not tell you immediately why they're there. That is part of what makes the underwater caves so powerful. They preserve evidence from different worlds that have occupied the same space. In one period, the cave was dry. Animals moved through it. Humans may have entered it. Stalactites grew from the ceiling. Stalagmites rose from the floor. Dripping water left mineral deposits slowly, drop by drop. Later, sea level rose, the water table rose with it, and the cave flooded. What had been an underground chamber became an underwater chamber. What had fallen, been placed, or died there remained. The water sealed the room in a new condition. A diver entering such a place today is not simply swimming through geology. They are moving through a flooded record of climate change, sea level change, animal life, human movement, ritual behaviour, and survival. It is a strange kind of museum, because the museum is not arranged for visitors. The visitor must adapt to the museum. The floor is not a floor to walk on. It is a surface that may hold evidence. The wall is not just a wall. It may carry mineral records. The dark space ahead is not only unknown passage. It may contain something that has not been disturbed for thousands of years. The Smithsonian Magazine article described Yucatan's cenotes and underwater caves as time capsules, preserving remnants of Maya culture and fossils of extinct megafauna. That phrase is useful because it captures the central idea. These caves did not simply hide objects, they slowed down their destruction. The article explains that the caves went through repeated cycles over long spans of time. During ice ages, when sea level was lower, caves that are now underwater could be dry. During warmer periods, when sea level rose, they flooded again. The last major flooding of shallow caves in the region happened around 8,000 years ago. That means a diver moving through some of these flooded passages is entering spaces that once belonged to a very different landscape. It is worth pausing on that difference. Today, the Yucatan can bring to mind jungle, turquoise coast, heat, resorts, ruins, and cenotes with clear water. But when some of these caves were dry, the region would not have looked exactly like it does now. Sea levels were lower. The coastline was farther away in some areas. The landscape around what is now the Caribbean coast could have been drier and more open. Cave entrances that are now submerged or hidden by water may have been reachable on foot. Animals entered. People entered. The cave was not an underwater tunnel then. It was a dry chamber in a different world. So when human remains are found deep inside a flooded cave, the first question should not be whether someone swam into a dangerous underwater passage thousands of years ago. In many cases, they did not need to. The passage was dry when they entered. The flooding came later. This is a simple point, but it changes everything. A skeleton in a submerged chamber may be evidence of an ancient fall, a death in a dry cave, a body placed intentionally, or some other human action before the water rose. The modern difficulty of reaching the spot does not tell us how difficult it was in the past. The cave has changed. One famous example from the Yucatan system is Hoyo Negro, often translated as black hole. A deep submerged pit where divers found the skeleton of a young woman now known as Naya, along with remains of extinct animals. Naya lived roughly 12,000 to 13,000 years ago. Her remains became important because they helped researchers study early people in the Americas. But before she became a scientific case, before she became part of museum discussions, DNA studies, and documentaries, she was a person who died in a cave when that cave was not the flooded place divers see today. That human fact sits beneath the scientific importance. The cave preserved her, but it did not reduce her to a specimen. Good archaeology has to remember both things at once. The same kind of respect applies to animal remains. Yucatan's caves have preserved bones of extinct animals from the late Pleistocene, including large mammals that no longer live there. These can include animals such as giant ground sloths, gomphotheres, saber-toothed cats, and other Ice Age fauna reported from cave contexts in the region. When divers find these remains, they are seeing evidence of a lost ecosystem. The bones show that the cave was once part of a landscape used by animals that walked, hunted, fed, or accidentally fell into openings. Some may have entered seeking water, shelter, or escape. Some may have fallen into pits. Some may have died elsewhere and been moved by water or collapse. Each find needs context before it becomes a story. Context is the quiet word that matters most here. A bone alone can be interesting. A bone in place is information. Its position, depth, condition, mineral coating, nearby sediment, relation to other bones, and distance from entrances all help researchers understand what happened. Was the animal complete or scattered? Were there cut marks? Was the bone moved by water? Did it fall into a pit? Was it associated with human activity? Was the chamber dry at the time? What was the water level then? What is the age of the surrounding deposits? These are the questions that turn a find into evidence. This is why cave divers who encounter remains must not treat them like souvenirs or decorations. Moving an object can destroy part of its meaning. A bone taken out of context may still be a bone, but the scene around it has been damaged. Archaeology underwater is especially delicate because the environment already makes everything harder. Visibility can change, sediment can rise, objects may be fragile. A careless fin kick can disturb the floor. Even a small movement can scatter the relationship between items. Underwater, the past is not only old, it is physically vulnerable. The caves preserve, but they do not protect themselves from modern mistakes. This is one reason trained documentation matters. Divers and archaeologists use photography, video, mapping, measurements, 3D modelling, and careful sampling. They may record where an item lies before touching anything. They may leave material in place if removal is not necessary, or if conservation cannot be done properly. When objects are recovered, they often require special treatment because something preserved underwater can deteriorate quickly once exposed to air. The cave gave it stable conditions. The surface can be harsher than the dark. There is a soft irony in that. People often imagine the surface as safety and the cave as danger. For the diver, that can be true. But for an ancient object, the cave may be the safer place. Bring it up without care, and the ordinary world begins to break it down. Wood can warp or crumble. Bone can dry and crack. Metal can corrode differently. Organic material can decay. The archive below is not convenient, but it has kept some things intact precisely because it is difficult to reach. Among the most striking finds in Yucatan cenotes are traces of Maya activity. Some cenotes contain ceramics, offerings, tools, ornaments, and human remains linked to ritual use, settlement, or later activity. The famous sacred cenote at Chichen Itza has long been associated with offerings, including objects of jade, gold, copper, shell, wood, textiles, ceramics, and human remains recovered through past dredging and archaeological work. That site is not the same as every cenote, and it would be wrong to assume all cenotes were used in the same way. But it shows how deeply these openings could matter in Maya life. To understand offerings in cenotes, it helps not to separate practical water from sacred water too sharply. In the Yucatan, water was life. During dry seasons, cenotes could be essential freshwater sources. The Maya also connected caves and cenotes with the underworld, with rain, with fertility, with death, and with renewal. The rain god Chake was especially important in relation to water and agriculture. If a community depended on rain and underground water, then a cenote was not just a convenient hole. It was a place where life depended on forces that could not be fully controlled. Offerings make sense in that setting. A vessel placed in water, a valuable object deposited in a cenote, or a human sacrifice at a major sacred site cannot be understood as random disposal. These acts belong to systems of belief, obligation, fear, gratitude, power, and petition. They were ways of communicating with deities, ancestors, or the underworld. They may have asked for rain, fertility, protection, political legitimacy, or renewal. The exact meaning of each offering depends on the site and context. The important point is that cenotes were not empty scenery around Maya civilization. They were active places in its religious and social life. At the same time, not every object in a cenote is an offering. This is another place where careful interpretation matters. A pot may have been dropped accidentally. A tool may have been lost. A body may represent sacrifice, burial, accident, violence, or later disturbance. Natural processes can move material. Flooding, collapse, sediment movement, and human activity can change a site. Archaeologists must resist the temptation to make every find dramatic. The truth is often more complicated and more valuable. The Smithsonian article mentions that artifacts and human remains from Maya civilization have remained undisturbed in deeper caves for centuries, visible to explorers. It also notes that evidence in cenotes points to human presence in the area dating back more than 13,000 years. That means the caves hold more than one human story. There is the very ancient story of Paleo-American individuals and early populations. There is the later story of Maya settlement, water use, ritual, and offerings. There are also colonial and more recent objects in some caves, including items from historical periods much closer to us. The archive is not one book. It is a shelf of books stacked without labels, some pages wet, some missing, some written in stone. A diver may pass from one kind of time into another in the same system. A fossil animal bone from the Ice Age, a human remain from deep prehistory, a ceramic vessel from Maya ritual, a more recent object from the colonial period. The cave does not arrange these by era. It holds them according to where they entered, fell, were placed, or were carried. The human mind wants a clean timeline. The cave gives a landscape. That makes interpretation challenging, but also rich. Researchers can study radiocarbon dates, uranium series dating of mineral deposits, DNA, stable isotopes, tool marks, ceramic styles, sediment layers, and cave morphology. They can ask what the cave entrance looked like at a given time. They can reconstruct ancient water levels. They can model how sea level rise flooded passages. They can compare human remains with other early American populations. They can examine how Maya offerings relate to drought, political power, pilgrimage, or local ritual practice. The cave holds evidence for all these questions, but the evidence has to be collected with patience. In Hoyo Negro, for example, water level reconstruction helps show that the chamber was dry when Naya and the animals entered. Later flooding placed the remains deep underwater. That explanation is not guesswork based only on the fact that the cave is now wet. It comes from studying the cave's geology, water levels and deposits. This is the kind of work that turns an astonishing discovery into a reliable story. Recent discoveries continue to show how much remains to be understood. In 2026, the Associated Press reported on a prehistoric skeleton found in a flooded cave along Mexico's Caribbean coast, recovered after being found deep inside a cave system near Tulum. The archaeologist involved said its distance from the entrance and depth suggested it must have entered when the cave was dry, at least 8,000 years ago. Its position on a sediment dune in a narrow interior chamber suggested it might have been intentionally placed, perhaps as a funerary deposit. That interpretation may develop as analysis continues, but it shows how these caves are still producing evidence that changes the picture of early human presence and behaviour in the region. The AP report also noted that this was the 11th such skeleton found in caves between Tulum and Playa del Carmen over about 3 decades, and that some earlier skeletons date to around 13,000 years ago. That number is small enough to feel fragile. 11 individuals across decades of exploration. Each one matters. Each one can add to understanding of migration, adaptation, burial practices, cave use, and the changing environment of the peninsula. But each one also reminds us that these discoveries are not endless. They can be damaged, they can be looted, they can be disturbed by development, pollution, or careless access. This is where the archive below becomes an ethical issue, not only a scientific one. The caves are full of evidence, but they are also under pressure. Tourism brings people, development brings roads, waste, construction, vibration, pollution, and groundwater change. Large infrastructure projects can affect caves and aquifers if they are not carefully planned and monitored. The AP report described concerns about impacts from the Maya train construction in the region and noted efforts to designate the area as a protected zone. Whether one is thinking about fossils, human remains, water quality, or living cave species, protection is not a decorative idea. It is the condition that allows future study to happen. The problem is that caves are easy to undervalue because they are hidden. A forest can be photographed from above. A reef can be filmed in bright water. A cave system under limestone is harder to show. People may not feel the loss of a passage they have never seen. But if a cave roof is damaged, if a sediment layer is disturbed, if a cenote is contaminated, if an archaeological context is looted, the loss may be permanent. The archive does not have backup copies. There is also a human sensitivity around remains. Ancient bones are scientific evidence, but they are also the remains of people who lived and died. They may belong to deep ancestral histories, cultural identities, and communities. Different regions and institutions have different laws and practices for handling such remains, but the basic respect should not be difficult to understand. A skeleton is not a prop for adventure. It is a person's body preserved by unusual conditions. The fact that the individual lived thousands of years ago does not erase that. The same respect should extend to Maya offerings. Objects placed in cenotes were often made with skill, value, and purpose. A jade bead, ceramic vessel, carved object, or wooden artifact may have been part of a relationship between people and the sacred landscape. Removing it without documentation steals not only the object, but the meaning that could have been understood from its location. Looting turns history into decoration. Careful archaeology turns it into knowledge. The quiet archive below is therefore not quiet because it has nothing to say. It is quiet because reading it requires silence, discipline, and restraint. The cave does not reward rushing. A diver must move slowly to avoid stirring silt. A researcher must document before interpreting. A conservator must stabilize before displaying. A community must decide how access and protection should work. Every step asks for patience. That patience is appropriate because the archive itself was made slowly. Limestone dissolved over vast spans of time. Sea levels rose and fell over glacial cycles. Animals entered dry caves. Humans explored, used, feared, honored, or avoided them. Maya communities placed offerings in certain waters. Flooding sealed spaces. Minerals coated bones. Sediment settled. Darkness kept the record out of ordinary reach. Then, many centuries later, divers returned with lights. The first sight of a bone underwater must be unforgettable, not in a loud way, more like the mind suddenly becoming very still. A pale curve on the floor, a skull partly covered in mineral, a long bone resting near stones. The knowledge that this is not just an object, but a message from a time when the cave had a different climate, a different entrance, a different relationship with the surface. The diver cannot ask the cave directly what happened. The cave answers only through evidence. A good archive is not always a place of certainty. Sometimes it is a place where uncertainty becomes more precise. Before a discovery, the past may be blank. Afterward, there are better questions. How old is this remain? Was the cave dry? Was the person placed here? Was the animal trapped? How did water levels change? What does the DNA show? What does the sediment show? Does this object belong to daily life, ritual, accident, or later disturbance? The mystery becomes sharper. That is progress. The underwater caves of Yucatan still hold many such questions. Some passages remain unmapped. Some known passages have not been fully studied archaeologically. Some finds may be visible but not recovered. Some sites are too fragile. Some areas are threatened before researchers can document them. The archive is large, but access is limited. It is not enough to know that evidence exists. It must be protected long enough to be understood. For a sleep-bound listener, all of this can settle into a slow scene. A cave chamber, now flooded, once dry. On the ceiling, formations that grew from dripping water in air. On the floor, sediment resting where it settled after the water rose. A bone lies partly hidden. A ceramic fragment sits nearby, but from another time entirely. A diver's light passes over both, not touching, only seeing. The water holds everything in place. The cave gives no explanation, but it keeps the evidence safe for those careful enough to read it. And above that cave, the jungle continues. Rain falls, roots grow, people swim in nearby cenotes. Roads hum. Birds call at dusk. The past remains below, not separated from the present, but layered beneath it. This is the strange gift of the cenotes. They are entrances to water, yes. Entrances to geology, yes. But they are also entrances to memory stored outside the human mind, in places where darkness and water have done what libraries try to do. They have kept the record. Ahead, that record leads us into the beliefs that gave cenotes some of their deepest meaning. Not only as wells, not only as cave entrances, not only as archives, but as thresholds. To the Maya, these openings could connect the human world with Xibalba, the underworld, a realm of gods, ancestors, death, rain, and renewal. The bones and offerings below do not make full sense without that older understanding of sacred water, sacred caves, and the doorway beneath the ground. After the bones and offerings, the cave no longer feels like only a natural place. It becomes a place where people once made choices. Someone carried a vessel into the dark. Someone stood near water and left something behind. Someone approached a cenote not only because it was useful, but because it meant something. To understand why, we have to stay with the Maya world for a while, not as a quick legend added for atmosphere, but as a way of seeing the land that shaped real actions. For many Maya communities, caves and cenotes were not ordinary holes in the ground. They were places where the human world touched other parts of existence. They could be connected with rain, fertility, death, ancestors, gods, and the underworld. This does not mean every cenote was treated in exactly the same way, or that every person in every period held one identical belief. Maya civilization covered a large area and lasted a very long time, with many languages, cities, traditions, and changes over the centuries. Still, across the Maya world, caves and water-filled openings often carried strong religious meaning. They were not simply useful landforms, they were thresholds. The word most people know today is Xibalba. It comes especially from Quiché Maya tradition, preserved in the Popol Vuh, and it is often translated as the place of fear or place of fright. In popular writing, Xibalba is often used broadly for the Maya underworld, though in Yucatan there were also other names and local traditions. That difference matters, because the ancient Maya world was not one single voice, but the idea behind it is still useful here. The underworld was not just a place below the ground. It was a realm connected with death, power, danger, transformation, and sacred beings. Caves and cenotes gave that realm a visible entrance. That is easy to understand when you stand at a cenote. Even without knowing the mythology, the place feels like an opening between worlds. Above there is heat, light, trees, insects, voices, and the ordinary business of being alive. Below there is cool water, stone, darkness, echo and depth. A person does not need a priest or a carved inscription to notice the change. The body notices first. The air cools. The sound changes, the light weakens. You step down, and the surface world becomes less immediate. For people who already understood the earth as layered with sacred meaning, that physical change would not have been just scenery. It would have confirmed that the place was different. In the Maya view, the world was often understood as structured in levels, with the human world, the heavens, and the underworld linked through sacred places and directions. Mountains, caves, trees, temples, and bodies of water could all take part in this structure. A cave was not only a gap in rock, it could be the inside of the earth. A cenote was not only water, it could be a route downward. In a landscape like northern Yucatan, where water often came from below, this was not an idea far removed from daily life. The underworld was not only in stories, it was beneath the village, beneath the forest, beneath the stone steps leading down to the well. That closeness may be one reason cenotes were treated with such care. They were practical and sacred at the same time. People needed water to live. Crops needed rain. The dry season could become dangerous. Drought could threaten communities. In this setting, water was not a background detail. It was survival. If rain failed, food failed. If wells dried or became difficult to access, life became harder. So it makes sense that rain gods, water sources, caves, and cenotes would be tied together in belief and ritual. The rain god, often called Chac, was especially important in Yucatan. Chac was associated with rain, thunder, lightning, and agriculture. In some traditions, rain beings were understood to live in caves, mountains, forests, and cenotes when they were not bringing rain. This is not a strange idea when you think about the physical world around people. Clouds can seem to gather near mountains. Mist can rise from cave mouths. Cool air can come out of openings in the earth. Water can appear from holes in stone. To a modern scientist, these are hydrological and atmospheric processes. To the Maya, they could also be signs of where powerful beings lived and acted. That does not make the Maya view simple or childish. It was an organised way of understanding dependence. People knew water mattered. They knew it could not be commanded like a household tool. Rituals were one way of negotiating with forces that humans could influence only partly. If you depend on rain, you make offerings to rain beings. If you depend on cenotes, you treat them as more than wholes. If a cave is thought to open into the domain of gods or ancestors, you do not enter it casually, the way someone today might wander into a garage looking for a screwdriver. This is where offerings come back into the story. Objects found in cenotes and caves can include ceramics, jewellery, incense burners, stone tools, shells, wooden items, and in some cases human remains. The meaning of these objects depends on the site. Some may be offerings, some may be part of ceremonies, some may be remains of everyday use, some may have entered by accident. But when archaeologists find repeated deposits in deep or difficult places, especially objects placed in cracks, pools, or chambers, the pattern suggests purposeful activity. People were not always just passing through. They were going in for reasons. Those reasons could be connected with rain, fertility, renewal, ancestors, power, or communication with the beings of the underworld. In some Maya rituals, breaking or piercing objects may have been part of releasing or changing their spiritual role. Ceramic vessels found with deliberate holes, sometimes called killed vessels by archaeologists, show that objects were not always placed intact for ordinary use. They could be transformed before being deposited. That is a very different relationship with objects from simply throwing away broken pottery. It suggests intention. Inside a cave, intention becomes harder to ignore. Think of the practical effort required. Someone had to enter. Sometimes they had to carry light. Torches would have smoked against the ceiling. The floor might have been uneven. The air could be damp. There could be narrow passages, pools, drops, bats, insects, and darkness beyond the torchlight. If a person carried an object deep inside and placed it in a specific location, that action cost effort. It took time, knowledge, and probably permission or ritual purpose. A cave does not receive a deposit by accident when the deposit is far from daylight. The sensory experience must have mattered too. A cave changes how a person feels. Sound echoes. The air is cooler. Shadows move strangely with firelight. A drip from the ceiling can sound louder than expected. A passage can narrow enough to make the body slow down. A chamber can suddenly open and make the torchlight feel small. If people entered for ritual purposes, the cave itself helped create the experience. It removed them from the ordinary day. It put them in a setting where darkness, stone, water and sound made the world feel different. Modern researchers have pointed out that caves can produce conditions of darkness and near silence that might support altered states of attention or ritual experience. You do not need to exaggerate this. A person does not need to hallucinate to be changed by a cave. Even a short time underground can sharpen awareness. You listen more. You watch your step. You become aware of your breathing. The outside world is not gone, but it is far away. For the Maya, this physical removal from daylight may have matched the religious idea of entering a threshold space. A cenote adds water to that threshold. Water reflects light, hides depth, preserves objects, and creates a boundary the body must cross. To enter water is already to change condition. You go from dry to wet, from standing to floating, from breathing freely to holding breath or relying on skill. In ancient Maya writing and later interpretation, water could be connected with death and transition. National Geographic has described cenotes as windows into the underworld and as a crossroads between the living and the dead. Even if we keep the language careful, the connection makes sense. A deep pool in a cave is an entrance you can see, but not fully know. At Chichen Itza, the sacred cenote is one of the best-known examples of a cenote with strong ceremonial importance. Objects recovered from it over the years included gold, jade, copper, shell, ceramics, wood, textiles, and human remains. The site was not just a convenient water source. It was a place where valuable materials were deposited, sometimes from distant regions, showing that its importance reached beyond the immediate local community. Offerings placed there were part of a larger religious and political world. A ruler, priest, pilgrim, or community might interact with the cenote as a powerful place where gifts could be given to beings beyond ordinary human reach. It is important to speak about human sacrifice carefully. It did occur in some Maya contexts, including traditions and evidence associated with caves and cenotes, but it should not be treated as the only thing that mattered or used as a cheap shock. Maya religion was not simply violence in a dramatic setting. It included agriculture, calendars, ancestors, rulership, offerings, music, incense, bloodletting, pilgrimage, feasting, and the management of relationships between humans and sacred forces. Human remains in cenotes can have different explanations depending on context. Some may relate to sacrifice, some may be burials, some may be accidents, some may come from different periods. The respectful approach is to let evidence guide the story. The underworld itself was not only a simple version of hell. That is another common misunderstanding. In Christian-influenced descriptions, underworlds are often framed as places of punishment. Some colonial sources interpreted Maya beliefs through that lens, which can distort what they were seeing. In the Popol Vuh, Xibalba is dangerous and frightening, ruled by powerful beings who test and harm humans, but it is also a place with houses, roads, trials, and a kind of social order. It is not merely a pit of fire. It is a realm with rules, beings, and stories. When modern people use the word underworld, we should not automatically imagine one familiar religious model. Maya ideas were their own. One of the most famous stories connected with Xibalba is the descent of the hero twins in the Popol Vuh. The twins enter the underworld, face trials, trick the lords of Xibalba, die, return, and eventually defeat the underworld powers. This story is not about Yucatan cenotes specifically, but it shows how the Maya underworld could be imagined as a place of danger, testing, transformation and return. The route downward is difficult, but it is not meaningless. The underworld is a place where change happens. That idea fits caves very well. A cave entrance is a real route downward. The body can go in and come out. The person who enters is temporarily removed from daylight and ordinary society. If they return with water, clay, a vision, ritual authority, or simply the completion of a ceremony, the cave has functioned as more than a hole. It has become a place of transition. Not all cave activity was ceremonial in the narrow sense. Archaeological studies have found evidence of practical activities too, including water collection, clay mining and other uses. But in Maya settings, practical work and ritual meaning could overlap. A person collecting water from a cave might still understand that water as pure or sacred. A person mining clay underground might still treat the place with caution. The modern habit of separating utility from belief may not fit the ancient experience very well. A place can be useful because it is sacred, and sacred because it is useful. This is especially true with water. Some descriptions from Yucatan speak of cenote water as zuhui ha, often translated as pure or virgin water. Water from a cenote was not only wet, it could be understood as clean, healing, powerful, or ritually important. If the water came from below, from a hidden source, protected by stone, then its meaning could be different from surface water. In a dry region, a cool, clear pool at the bottom of a cavern would naturally gather practical and spiritual attention. Cenotes could also be places of community memory. A settlement near a cenote might depend on it for generations. Children would learn its name, families would know its paths and dangers, ritual specialists might know stories attached to it. Offerings might be made in times of drought or crisis. Deaths, accidents, ceremonies, and daily water collection could all become part of the place's history. Over time, the cenote would not be just a feature in the land. It would be a known personality in the community's world. This is why modern tourism can sometimes flatten the meaning of cenotes. A visitor sees water, takes a photo, swims and leaves. There is nothing wrong with enjoying the beauty of a cenote when it is done respectfully. But the place is older than the visit. It has geological history, archaeological history, local history and sacred associations. A cenote is not just a natural swimming pool with better lighting. It is a place where people drank, prayed, feared, worked, remembered, and sometimes gave up objects of great value. The doorway idea also affects how we think about the underwater tunnels. To modern divers, the tunnels are cave systems, hydrological routes, and research sites. To ancient Maya people, a cave or cenote could also be an entrance into the realm below. That does not mean they knew the full underwater extent of the passages, especially when many were dry or differently flooded in the past. But they did not need a modern cave map to understand the importance of an opening. The entrance itself was meaningful. The visible descent was enough. In some caves, archaeologists have found evidence of rituals deep inside, far from daylight. That tells us that darkness did not simply prevent use. In some cases, it may have been part of the reason for going. The deeper a person went, the farther they moved from ordinary space. Objects placed in cracks, pools, chambers, or near formations suggest that particular features inside caves mattered. A stalagmite might resemble a tree, pillar, or figure. A pool might represent water of special power. A narrow passage might feel like a birth canal or route into the earth. A chamber might become a ritual room without needing walls built by human hands. This also helps explain why formations were sometimes important. Stalactites, stalagmites, columns, flowstone and dripping water can make a cave look alive, even though the processes are mineral and slow. Water drips, stone grows, shapes emerge. To a person carrying firelight, these forms might suggest trees, bodies, teeth, faces, animals or beings. Modern science describes calcium carbonate deposition. Maya ritual thought may have described sacred stone, living earth, or the presence of beings. Both observations start with the same physical forms. The underworld connection also gives another meaning to the bones we discussed before. Human remains in a cave or cenote are not only archaeological evidence of death. They may belong to beliefs about transition, sacrifice, burial, communication, or placement near sacred water. Animal bones too may have carried meanings depending on species and context. A jaguar, deer, bird, snake, or dog could all have symbolic roles in Mesoamerican thought. Again, context matters. Not every bone is an offering. But in a place already understood as a doorway, remains take on possibilities that would not apply in an ordinary trash pit. There is something deeply serious about placing an offering into water. Once released, it is gone from ordinary use. A jade object dropped into a cenote cannot be easily retrieved. A vessel placed in a cave pool is removed from daily life. A sacrifice, if that is what took place, is even more final. These acts show that the place was understood as capable of receiving. The water was not a dead container. It was a root, a mouth, a connection, or a presence. The name doorway is useful here because a doorway has two sides. It is not only an entrance from the human world into the underworld, it is also a place where the underworld can touch the human world. Rain can come, fertility can return, ancestors can be contacted, dangers can emerge, blessings can be requested. The relationship moves both ways. A cenote is not merely a hole people look into, it is a boundary people interact with. For the Maya, boundaries were often powerful. Dawn and dusk, caves and entrances, crossroads, water surfaces, temple doorways, mountain openings, and calendar transitions could all be moments or places where ordinary categories loosened. A cenote at twilight, with the surface reflecting the last light and the depth turning dark, would be exactly the kind of place where such thinking feels physically grounded. It is not hard to see why people gave such places stories. This does not mean every Maya person approached every cenote with fear. Daily life has a way of making even sacred places familiar. People may have drawn water, washed, talked, carried jars, watched children, repaired steps, and gone home tired. The sacred and ordinary can coexist. A church bell can mark a holy day and also tell a town what time it is. A cenote can be a sacred doorway, and also the place where someone fills a container because dinner still needs cooking. Human life is usually made of both at once. That mixture is important for the tone of this story. We're not entering a fantasy underworld. We're trying to understand how real people lived with real water in real limestone landscapes. Their beliefs were not decorations added to geology. They were part of how they understood dependence, danger, fertility, death, and the hidden systems beneath their feet. A modern scientist may map groundwater flow. A Maya ritual specialist may speak to rain beings. Both are responding to the fact that water comes from places humans cannot fully control. Today, many Maya communities still regard caves, mountains, springs, and other natural places as sacred, though beliefs and practices vary widely. Ancient traditions did not simply vanish. They changed, survived, mixed, and continued in different forms. This matters because cenotes are not only archaeological sites from a finished past, they are part of living cultural landscapes. Respect for them should include living people, not only ancient objects. As we move through this part of the story, the word Xibalba should not be used as a spooky label. It should be understood as one way of naming the deep significance of caves and the world below. The underworld was frightening, yes, but not only frightening. It was dangerous because it was powerful. It was connected with death, but also with rain and life. It was below, but not separate. It was hidden, but reachable through certain places. A cenote could be one of those places. So imagine a Maya person approaching a cenote before dawn. The air is not yet hot. The surface of the water is dark. The stone sides hold the coolness of night. Perhaps the visit is ordinary, a trip for water. Perhaps it is ceremonial, with incense, words, offerings, and others gathered nearby. Perhaps it is both. The person looks down and sees not a tourist attraction, not an adventure site, not a hydrological sample point, but a place that gives water and reaches into the earth. The act of approaching it already has meaning. Below that same surface, centuries later, a diver's light moves through the flooded passage. The modern diver sees limestone, halocline, bones, pottery, and cave-adapted life. The scientific terms are different, the equipment is different, the questions are different. But the basic recognition remains surprisingly close. This place is not ordinary. It connects things. It connects rain to groundwater. It connects settlement to survival. It connects geology to ritual. It connects the living to the dead. It connects ancient offerings to modern research. It connects a visible pool to tunnels no one from the surface can see. And somewhere in those tunnels, beyond the areas tied to human story, there are animals that have no need for sunlight, no interest in mythology, and no awareness that humans have been arguing for centuries about what the underworld means. They live in the dark water because the dark water is their world. Small fish, crustaceans, microbes, blind or pale creatures adapted to caves. Life that does not ask whether a place is sacred before finding a way to survive there. The Maya doorway leads us deeper, not only toward gods and ancestors, but toward the living residents of the underground water itself. The doorway into the underworld does not lead only to bones, offerings, and old stories, it also leads to life. That may seem surprising at first. A flooded cave beyond the reach of daylight does not look like a promising place to make a living. There are no green plants waving in the current, no coral gardens, no sunlit surface full of insects, no fallen fruit bobbing cheerfully along like a snack delivery service. There is stone, water, darkness, and silence. Or at least the kind of silence that belongs to places where no wind reaches. To a human visitor, it can feel almost empty. But the dark water is not empty. It has residents. Some are small enough to be missed unless a diver knows how to look. Tiny shrimp move over rock surfaces or near the ceiling. Little crustaceans drift or crawl in the water column. Worms, isopods, amphipods, copepods, and other invertebrates occupy specific parts of the cave, each one adapted to a life that would seem impossible to most surface animals. Some are pale or almost transparent. Some have reduced eyes or no useful eyes at all. Some move slowly, saving energy in an environment where food is not thrown around carelessly. A cave is not a buffet. It is more like a very strict kitchen, where every crumb has already been assigned a purpose. Then there are the fish. The Yucatan aquifer is home to unusual cave fishes, including the Mexican blind brotula, Typhlias persei, sometimes called the dama blanca ciega in Spanish, and the blind swamp eel, Ophisternon infernale. These are not colourful reef fish designed to impress photographers. They are pale, secretive animals shaped by darkness. The Mexican blind brotula has no useful eyes and depends on other senses. The blind swamp eel is long, pale, and adapted to life in the hidden waters of limestone caves. If a person expects cave life to look dramatic, toothy, and theatrical, these animals may feel quiet by comparison. But quiet does not mean simple. In fact, their bodies are records of evolution, doing careful work under very difficult conditions. Life in a cave asks different questions from life at the surface. On the surface, eyes are useful because sunlight is useful. Colour can help with warning, attraction, camouflage, and communication. Fast movement can matter because food and predators may be everywhere. In total darkness, some of these rules change. Eyes are expensive tissue if they do not help. Pigment may not matter much if nothing can see you. Energy is limited, so wasting it is a bad idea. A cave animal does not need to look impressive to us. It needs to survive in a place where the usual surface economy has been shut down. This is why many cave-adapted animals share certain features. They may lose pigment. They may lose or reduce eyes. They may develop longer antennae, sensitive hairs, chemical sensing, or vibration detection. They may have slower metabolisms, they may reproduce slowly, they may live in low numbers, they may be found only in one cave system, one region of the aquifer, or even one part of one cave. The word for animals that live entirely in groundwater is stegobiont. It is a useful term, though it does sound a little like a small robot from a science fiction film. Stegobionts are tied to subterranean water. The cave is not a place they visit, it is their world, and their world has zones. Near a cenote entrance, sunlight may reach the water, algae can grow, leaves and insects can fall in, birds, bats and other animals may bring organic material. This entrance zone is connected to the surface in obvious ways. It can be brighter, richer and more variable. Farther in, there may be a twilight area, where light weakens and surface influence fades. Beyond that is the true dark zone, where there is no photosynthesis and no daily rhythm of sunlight. In this region, life cannot depend directly on plants growing there, because plants need light and the cave is not providing any. The cave, in a very firm tone, has declined to install windows. So where does the food come from? Some food arrives from above. Leaves, soil material, small organisms, bat guano, and dissolved organic matter can enter through cenotes, cracks, roots, and groundwater flow. Rainwater percolates through the forest floor and limestone, carrying traces of the surface world downward. In some places, organic matter from the jungle becomes part of the cave food web. This means the animals below are connected to the health of the forest above. The cave may look sealed, but it is not independent. Damage at the surface can become hunger below. But the caves also have another source of energy that makes them especially interesting. In the dark zones of Anchialan caves where fresh and salt water mix and sunlight cannot fuel plants, microbes can use chemical energy. This is called chemosynthesis. Instead of plants using sunlight to make food, certain bacteria use chemical compounds as an energy source. In Yucatan caves, recent research has focused on methanotrophic bacteria that consume methane, and on tiny cave shrimps of the genus Deflatia that graze on microbial growth. These shrimp can help move energy from microbial production into the animal food web. That may not sound dramatic at first. A shrimp scraping bacteria from cave surfaces does not have the obvious grandeur of an asteroid impact or the emotional weight of ancient remains. But in the cave ecosystem, that little shrimp is doing something enormous. It is helping convert microbial energy into animal body tissue that other animals can eat. It becomes a link. Microbes use chemical energy. Shrimp graze on microbes. Larger predators may feed on shrimp. The food web continues in the dark. In a sunlit forest, a leaf can be the beginning of a food chain. In a cave, the beginning may be a microbial mat. That is a useful shift in perspective. We often imagine life as something that begins with sunlight because for us, sunlight is everywhere. Plants grow. Animals eat plants. Other animals eat those animals. People eat snacks while explaining the food chain with unnecessary confidence. But Earth has many places where life works differently. Hydrothermal vents in the deep ocean, caves, sediments, and other dark environments can depend on microbial chemistry. The Yucatan caves are not deep-sea vents, but they show the same broad lesson. Life does not always wait for sunlight. Sometimes it finds energy in chemistry and then builds a quiet community around it. The halocline plays a role here too. That shimmering boundary between fresh and salt water is not only a visual disturbance for divers, it can also mark a chemical transition. Different waters bring different substances, oxygen levels, nutrients, and microbial opportunities. Some species may be found near particular layers or depths. Research on Deflatia shrimps in Yucatan has shown that different species can occupy different dietary niches. One may rely more on decomposing vegetation and bacteria in shallower areas. Another may use organic material trapped near the halocline. Another may feed heavily on methanotrophic bacterial biomass near cave ceilings. The cave may look simple to the human eye, but the animals are dividing it into neighbourhoods. This is one of the most important things to understand about cave life. The ecosystem is not random, it has structure. Species are not sprinkled through the tunnels like pepper. They occur where the conditions suit them, near entrances, in deeper passages, near the halocline, on ceilings, in sediments, in zones with certain chemistry, or along routes where organic material arrives. A diver may see only darkness and rock. A biologist sees gradients, niches, and fragile relationships. In the Oxbelhar system, another major underwater cave system near the Caribbean coast, researchers studied the distribution of Anchialan cave fauna across a transect extending inland from the coast. They collected multiple crustacean species and found that the animals were not distributed evenly everywhere. Their locations related to the cave's environmental zones and distance from the coast. That kind of work helps explain why one cave section may contain certain animals while another does not. It is not enough to say there are cave shrimp in Yucatan. The better question is, which shrimp, where, at what depth, in what water chemistry, and connected to which food sources? That is where the science becomes careful. A cave ecosystem is not easy to sample. Researchers may need trained divers to collect tiny animals in difficult places. Samples must be handled carefully. Water conditions must be measured. Genetic analysis may be needed because animals that look similar can be different species. Stable isotope analysis can show what organisms are eating by examining chemical signatures in their tissues. This is how scientists can trace food sources without having to sit in a cave for weeks watching a shrimp have dinner, which would be both difficult and not especially polite. Stable isotopes are particularly useful because cave food webs can be hard to observe directly. In the dark, animals may be rare and small. Feeding may happen slowly or at night, though in a cave, night is not quite the same concept. Isotope signatures can show whether an animal's diet is tied more to surface-derived organic matter, microbial production, methane-based pathways, or other sources. In recent work on Tiflatia shrimps, researchers found evidence that these shrimps occupy distinct feeding roles and can act as key parts of the cave food web. That is a lot of responsibility for a small, transparent animal, but nature has always been comfortable giving important jobs to things humans barely notice. The Mexican blind brotula sits higher in the food web. It is often described as a top predator within parts of the Yucatan aquifer system. It feeds on crustaceans such as shrimp and mysids. It does not need vision in the ordinary sense. Instead, it uses other sensory structures to detect movement, vibration, and chemical cues. Imagine living in darkness so complete that vision offers nothing, and still being able to find food, avoid danger, reproduce, and move through flooded limestone. That is not a lesser form of life. It is life tuned to a different set of information. The blind swamp eel has its own adaptations. It is pale and eyeless, with an elongated body suited to hiding under stones, in mud, or within cave habitat. Fishbase notes that adults inhabit cave systems and that males build and guard nests or burrows. Even that small reproductive detail is remarkable. It means that in the dark water, in the hidden mud or stones of a limestone cave, parental behaviour is taking place. The cave is not merely a passage. It is a home where animals feed, reproduce, and maintain their life cycles. Because some cave species are rare, endemic, or restricted to particular habitats, they are vulnerable. Endemic means a species is found only in a specific region. If a cave species lives only in the Yucatan aquifer, and if the aquifer is polluted or disturbed, the animal cannot simply move to a nice new cave in another country and update its address. It is tied to that water. The Mexican blind brotula is listed as near threatened by IUCN according to catalogue sources, and the blind swamp eel is listed as endangered. These categories are not dramatic decorations. They reflect real concerns about limited habitat, water quality, human disturbance, and the difficulty of protecting animals most people will never see. Pollution is one of the main threats. In a karst aquifer, contaminants can enter quickly through cracks, sinkholes, sewage leakage, waste disposal, agriculture and development. Because caves depend on groundwater, anything that changes groundwater quality can affect the animals. Excess nutrients can alter microbial communities. Sewage can introduce bacteria and chemical changes. Pollution can reduce oxygen or change food webs. Sediment can smother habitat. Construction can damage cave ceilings or alter water flow. The animals below may be adapted to darkness, but they are not adapted to modern waste systems, making poor decisions above them. This is why protecting cave fauna means protecting more than the cave entrance. It means protecting the forest, soil, water recharge areas, wastewater systems, and land use above the cave. The phrase vertical integrity has been used by researchers to describe how surface and subsurface must remain connected in a healthy way. If the cave food web depends on organic matter filtering down from the forest, then removing or polluting that forest changes the cave. The darkness below depends on the sunlight above, not because light reaches the cave directly, but because the surface world supplies energy and chemistry. That is a very important idea. The cave is dark, but it is not separate. The shrimp grazing in darkness is connected to leaves decomposing above. The blind fish is connected to the shrimp. The microbes are connected to methane and organic matter moving through limestone. The freshwater lens is connected to rain. The halocline is connected to the sea. A decision made at the surface can move through the whole chain. This also means cave animals can serve as indicators. Their presence, absence, distribution, health, and diet can tell scientists something about the aquifer. If species disappear from a location, if community structure changes, or if chemical signatures shift, it may show that the system is being altered. Cave animals are not only strange and interesting, they can be witnesses. They record environmental change with their bodies and populations. There is also the matter of evolutionary history. Many hyaline cave animals belong to lineages that may be very old. Some have relatives in distant regions, suggesting ancient dispersal, shifting seas, changing coastlines, and long isolation. The Yucatan caves have acted as refuges, places where lineages could persist in stable darkness while the surface changed dramatically. Some species may have been isolated in groundwater systems for very long periods, gradually adapting to local conditions. Evolution in caves can produce forms that seem unusual to surface eyes, but the pattern is logical. In darkness, selection favours the senses and behaviours that work there. It is tempting to call these animals primitive, but that is misleading. A blind cave fish is not unfinished. Transparent shrimp is not an early draft. These animals are specialised. They have lost features that do not help and developed traits that do. Losing eyes can be an adaptation when eyes cost energy and provide no benefit. Losing pigment can be sensible when there is no light-driven need for colour. Slower movement can be efficient when food is scarce. Cave life is not backward, it is precise. Still, it is fragile. Many cave systems are stable in temperature, light and chemistry compared with the surface. Species adapted to stable conditions may not tolerate rapid change as well. If groundwater becomes polluted, warmer, more saline, lower in oxygen, or altered by nutrient input, cave animals may have limited ability to cope. They often have small populations and slow reproduction. Recovery from disturbance may be difficult or impossible. This is one reason researchers emphasize conservation. The underwater caves of Yucatan are not only scenic diving sites and archaeological archives, they are biodiversity reservoirs. Some animals, found there, occur nowhere else. Some may not even be described yet. New species can be discovered through careful sampling and genetic work. There may be organisms living in unmapped passages that scientists have not documented. To damage the aquifer before studying it fully would be like burning pages from a book before learning the alphabet. A diver moving through the dark zone may not see many animals at once. That is normal. Cave ecosystems are often sparse. The absence of obvious life does not mean life is absent. A shrimp may move away from light. A small crustacean may stay close to sediment. A microbe may be doing important work on a surface that looks like plain rock. A fish may be rare and hidden. The cave does not display its residents like an aquarium. It lets them live by the rules of darkness. There is a calm beauty in that. Not the showy beauty of reef fish flashing in sunlit water, but the quieter beauty of adaptation. A blind fish sensing a faint vibration. A shrimp scraping bacteria from stone. A tiny crustacean occupying a narrow chemical layer. A microbial mat feeding a food web without a single green leaf in sight. Life, reduced to careful essentials, continuing where a human would need tanks, lights, training, and a very serious conversation with common sense before entering. The animals also change how we think about the underworld. To the Maya, caves and cenotes could be doorways to sacred realms. To modern science, they are also ecosystems. These views do not cancel each other in the script of the landscape. A place can be sacred to people and habitat to animals. It can be a water source, an archive, a cave, a shrine, and a food web. The blind brotula does not know it lives in a place humans call mysterious. The shrimp does not know it supports a scientific paper. The microbes do not know they are part of a chemosynthetic route. They simply do what life does when given even a narrow chance. And that may be the most grounded wonder here. Life does not need grandeur, it needs conditions. A little energy, a way to reproduce, a habitat stable enough to persist, and time. The Yucatan caves provide darkness, water, chemistry, and shelter. Over generations, life adapted. Not loudly, not quickly, not for our convenience. It became pale, slow, sensitive, and hidden. As the diver's light moves across the cave ceiling, small shrimp may scatter or continue grazing. Farther away, a blind fish may sense the disturbance and vanish into shadow. In the sediment, tiny animals move where no casual visitor will ever notice them. On the rock, bacteria grow in thin films, turning chemical energy into the first step of a food chain. The cave remains dark, but the darkness is occupied. Above, the forest still matters. Rainwater still matters. The health of the soil still matters. The way towns handle waste still matters. The choices made by people who may never see a blind cave fish still matter to that fish. The dark water is not apart from the world. It is one of the places where the world's hidden connections become easiest to miss and hardest to repair once damaged. And beyond the known passages where these animals have been studied, the tunnels continue. Some routes have been mapped, some have been sampled, some have names, survey lines and data. Others remain beyond the last marker, past a narrow restriction, behind a collapse, under a forest no one has fully surveyed, or inside a water route too delicate or dangerous to enter. There may be more species there, more microbial communities, more bones, more clues about water movement, more evidence of how the caves formed and how they are changing. The creatures of the dark water teach us that the unknown is not always empty. Sometimes it is alive, small, pale, and moving slowly through a place where sunlight has never arrived. The dark water is alive, but it is not fully known. That is the thought that stays behind after the blind fish, the pale shrimp, the microbes, and the small animals that move through limestone passages without ever needing daylight. The cave is not an empty tunnel waiting for human attention. It already has its own residents, its own water movement, its own chemistry, its own slow changes. Human beings arrive late, carrying lights, reels, tanks, cameras, and the very human belief that if we can draw a line on a map, we have understood the place. The caves of Yucatan do not give themselves up that easily. A map of an underwater cave system looks clean when printed. Thin lines branch across a page. Numbers mark distances and depths. Names appear beside entrances and sections. Sac Actun, Oxbelha, Dos Ojos, Cuxbal, Nohochna Chich. The lines look certain, almost tidy. But every one of those lines represents a person going into an overhead environment where the surface is no longer directly above them, where a mistake can become serious very quickly, and where every new metre has to be earned slowly. The map looks calm because the danger has been translated into ink. Mapping a flooded cave is not like walking into a dry cave with a flashlight and notebook. Even dry cave mapping can be difficult, muddy, tiring and awkward. Underwater, everything becomes stricter. A diver enters through a cenote, ties into a guideline, checks equipment, moves through the passage, records distance and direction, watches depth, monitors breathing gas or rebreather function, keeps track of time, avoids damaging formations, avoids disturbing sediment, and constantly remembers that going in is only half the task. The second half is coming out. That may sound obvious, but in a cave, obvious things become rules. Every metre forward must be matched by a safe plan to return. Every new passage must be surveyed, not just enjoyed. Every lead has to be evaluated. A lead might be a dark opening at the edge of a chamber, a low tunnel beyond a restriction, a crack with water moving through it, or a place where the cave seems to continue behind fallen stone. Some leads open into large new passages, some end after a few metres, some are too tight for a diver to pass. Some may have strong flow, poor visibility, unstable rock, or fragile archaeology. The cave does not label them, it simply offers the possibility, and the diver has to decide what can be done safely. This is one reason so many passages remain unmapped. It is not only because no one has looked, it is because looking is hard. Some sections are far from the nearest entrance. Reaching them may require long penetration dives, scooters, staged tanks, rebreathers, support teams, and repeated trips. Some passages are shallow but silty, where one wrong movement can reduce visibility to almost nothing. Some are small enough that equipment must be adjusted carefully just to pass through. Some are protected, restricted, or on land where access is not simple. Some contain archaeological remains that should not be disturbed. Some may be biologically sensitive. Some are dangerous because they are unstable. Some are simply hidden under forest, waiting for someone to find the right small opening in the ground. And sometimes the passage is there, but the human body is the wrong shape for it. That is one of the odd facts of cave exploration. Water can move through spaces that humans cannot enter. A dye test, flow pattern, salinity change, or current may show that two systems are connected hydrologically. The water knows the route. But if the passage is too small, blocked, collapsed, or unsafe, divers cannot make the physical connection. In cave survey terms, that matters. A connection between mapped systems often requires a passable route, not only proof that water moves between them. This can be frustrating because the cave may be connected in every practical hydrological sense while still refusing to let a person through. It is a very stone-like kind of stubbornness. Recent exploration stories from Quintana Roo show how close and difficult these connections can be. In 2025, cave explorer Robbie Schmittner described connecting the Cuxbal system with the mother of all cenotes, creating a system of more than 120 kilometres, and noted that the combined system sat only about 31 metres from Sakaktoon at one lead. Water flow suggested connection, but the passages at the closest points were too tight for divers to pass, so the work continued by searching for alternate routes, other cenotes, and longer ways around the barrier. That is what exploration often looks like. Not one grand breakthrough every day, but many attempts, many blocked leads, and occasionally one small hole in the jungle that changes the map. The surface gives very little warning of this. A small opening in the ground may lead nowhere. It may drop into a chamber and stop. It may be full of debris, it may be too tight, too unstable, or too dry. Or it may open into a route that connects two known cave systems and changes the scale of the underground map. From above, these possibilities can look almost identical. Leaves, roots, stone, mosquitoes, and a hole just wide enough to make everyone involved question their life choices. Then someone enters carefully, and the hidden world either closes down or opens. This is why the Yucatan still has unmapped passages after decades of cave diving. The region is too large, the systems too complex, and the access points too unevenly distributed for exploration to be finished. Since the 1980s, divers have uncovered hundreds of caves and more than 1,000 miles of tunnels beneath the peninsula. Even with that enormous amount of work, many caverns remain uncharted. The numbers are impressive, but they should not create a false sense of completion. 1,000 miles of mapped passage does not mean the whole system is known. It means the known part is already huge. The Great Maya Aquifer project has described the underground realm as still being explored and charted, with its full extent unknown. By 2022, the total of mapped caves in the wider project area was described as about 1,650 kilometres. That is already an extraordinary figure. It is roughly the distance from Paris to parts of southern Spain, except instead of a road, with signs, fuel stops, and regrettable sandwiches, it is a maze of flooded limestone beneath jungle. And even after all that mapping, researchers involved in the project still describe the area as a place where much remains to be discovered and documented. This is not because explorers have been careless or slow. It is because the caves are complicated in exactly the wrong way for human convenience. They branch, they loop, they run parallel, they pinch down, they open into large chambers, then split into small side passages. They connect through restrictions. They may pass under land where no cenote entrance is known. They may be interrupted by collapse. They may continue below haloclines, through brackish water, through low tunnels, or past areas where sediment can ruin visibility. They do not form a neat underground subway system. If they had been designed by an engineer, the engineer would have been asked to attend several meetings. The shape of the caves is controlled by limestone, fractures, sea level history, fresh and salt water mixing, collapse, and groundwater flow. Different passages formed under different conditions. Some are broad phreatic conduits, shaped while filled with water under pressure. Some are fracture-controlled rooms. Some areas run roughly parallel to the coast. Some drain toward the Caribbean. Some are connected to cenotes that act as windows into the system. Others remain hidden because no roof has collapsed above them, or because the entrance is too small, blocked, or overlooked. The unmapped passages matter for more than records. It is easy to become distracted by length. Longest underwater cave. Second longest cave system. More kilometres. New connection. Bigger map. These records are exciting, but the real importance goes deeper. Mapping tells scientists where water moves. It helps identify which cenotes are connected. It helps explain how contamination may travel. It helps locate fragile ecosystems. It helps protect archaeological sites. It shows where development could damage a cave roof or pollute the aquifer. A cave map is not just an explorer's trophy. It is a safety document, a water document, an archaeological document, and a conservation document. In a karst aquifer, not knowing the route of water can be risky. If wastewater enters the ground, where does it go? If a construction project drills into limestone, what cavities lie below? If a storm sends runoff into a sinkhole, which passages carry it onward? If a cave contains ancient remains, how close is it to development? If saltwater intrusion changes the freshwater lens, which routes are affected first? These are not decorative questions. They affect people, animals, water quality, and heritage. The difficulty is that the underground system does not wait for the map to be finished before it starts responding to modern pressure. Tourism grows, towns expand, roads are built, waste systems lag behind. Large infrastructure projects cross karst terrain. Hotels and residential developments spread toward places where the aquifer is thin, connected and vulnerable. A passage may be unmapped when decisions are made above it. Later, divers may find the cave after the damage has already begun. That is one of the uncomfortable truths of hidden landscapes. They can be harmed before they are understood. The Associated Press reported in 2024 that scientists and environmentalists were concerned about damage to the Yucatan subterranean caverns, rivers, and cenotes from development and construction, including the Maya Train project. The report described an extensive hidden system already under pressure from development and mass tourism. That pressure makes mapping more urgent, not less. The blank spaces on the cave map are not harmless blanks. They may contain water routes, fragile species, archaeological evidence, or structural hazards. Unmapped does not mean unused by nature. A passage no human has entered may carry a large amount of fresh water. It may host cave-adapted animals. It may contain sediments that record sea level change. It may preserve bones from the Ice Age. It may connect two known systems through a route that changes how scientists understand regional flow. It may lie beneath a planned road. It may be narrow, dark, and unknown, but it still has a function. This is one of the reasons cave explorers often speak about their work with unusual patience. The public may see only the dramatic discovery. Two systems connected, a record broken, a new map released. But the work before that can be repetitive and physically demanding. Carrying gear through jungle, cutting paths, hauling tanks, checking small cenotes that lead nowhere, diving a promising lead that closes after 10 meters, returning to the same area again and again, waiting for conditions to improve, negotiating land access, training, repairing equipment, drawing maps, comparing surveys, looking at a tiny gap between known lines and deciding whether there is any safe way to close it. That is not the fast version of exploration, it is the real version. There is also emotional discipline involved. A cave diver must be curious enough to keep looking, but cautious enough to turn around. That balance is difficult. The cave encourages curiosity. A dark opening ahead always suggests more. A current through a crack suggests a route. A gap on a map suggests a connection. But safe exploration depends on knowing when not to push. The cave will still be there tomorrow. A person who ignores that fact may not be. The best explorers are not the ones who feel no fear. They are the ones who respect limits. Some unmapped passages will remain unmapped because they are too dangerous or too fragile. That is not failure, it is judgment. Not every place needs to be entered. Some archaeological contexts may be better documented remotely or left in place. Some biological habitats may be too sensitive for repeated visits. Some restrictions may be unsafe. Some caves may be better protected by not advertising their entrances widely. The goal of understanding does not always mean access for everyone. Sometimes protection requires restraint. Technology may help, but it will not remove all difficulty. Better underwater mapping tools, photogrammetry, 3D modelling, cave radios, improved lights, rebreathers, scooters, water chemistry sensors, dye tracing, remote imaging and environmental DNA sampling can all expand what scientists know. Drones and LIDAR may help on the surface. Geophysical methods may identify voids or structures underground. But flooded caves remain difficult places. A robot may not fit. A signal may not pass through limestone. A sensor may be lost. A model may need ground truth. Human divers, with all their limits, still remain essential in many sections. That creates a strange partnership between old and new exploration. A diver may use modern equipment and digital mapping, but the basic act is ancient in feeling, entering a dark opening to see what lies beyond. The difference is that today, the goal is not only discovery, it is documentation. The line added to the map must be accurate. The water sample must be labelled. The archaeological site must be recorded without damage. The species must be identified correctly. The conservation concern must be communicated before the place is lost. The unmapped passages also remind us that the Yucatan caves are not a finished wonder from the past. They are a continuing story. New discoveries still happen. New connections are still possible. Oxbel Har has been described in recent reporting as extending at least 524 kilometres, making it the longest known submerged cave system. Sac Acton remains one of the great mapped systems. Kuxbal and other systems continue to grow through exploration. Rankings may change, and new survey totals will likely replace old ones. That is part of the point. The map is alive because the work is alive, but the cave itself does not care about rankings. A passage is not more important because it makes a system longer by a kilometre. A small unmapped side tunnel may matter because it carries water, contains a rare animal, or holds a fragment of human history. A narrow crack may be scientifically important even if it cannot host a dramatic dive video. Exploration records bring attention, but understanding comes from detail. Imagine one such unmapped passage. It may begin beyond a known chamber, where the main line turns left and the mapped route continues. To the right, behind a low overhang, there is a darker slot. A little water movement can be felt there. Sediment on the floor is fine and pale. The ceiling is close. A diver shines a light into it and sees that the tunnel continues, but not comfortably. It may widen after a few meters, or it may close. It may lead to a new chamber, or it may lead to nothing passable. No one knows yet. The map stops at the edge of that uncertainty. That edge is where a lot of science begins. The blank space asks for care. First, is it safe? Then, is it fragile? Is there flow? Is there silt? Is there archaeology nearby? Is there enough visibility? Is there enough gas? Is the team ready? Can the route be surveyed accurately? Can it be done without damage? If not today, maybe another day. If not by a person, perhaps by a different method. The unknown is not an invitation to rush. It is an invitation to behave well. This is a good lesson beyond caves, although the cave teaches it with unusual firmness. Not knowing something does not give us permission to treat it as empty. The unmapped parts of Yucatan may contain exactly the evidence needed to understand the aquifer, protect water, explain ancient movement, or identify species found nowhere else. The dark passages are not blank because they lack meaning. They are blank because we have not reached them yet. Above the cave, life continues with very little awareness of the line ending below. Rain falls into soil. A town uses groundwater. A tourist swims in a cenote. A construction crew drills into limestone. A jaguar drinks at an opening in the forest. A shrimp grazes on microbial film in darkness. A diver studies a map and notices a gap. All of these actions belong to the same landscape. The hidden passages connect them more than anyone standing on the surface might guess. As we move toward the final part of this journey, the unmapped tunnels leave us with a clear feeling, but not a finished conclusion. The Yucatan underground is known and unknown at the same time. Enough has been mapped to show that the system is vast. Enough remains unmapped to keep the story open. Science has explained the main forces: limestone dissolution, karst collapse, sea level change, freshwater flow, saltwater mixing, impact-related structures, human use, biological adaptation. But explanation does not end exploration. It makes exploration more careful. Somewhere beyond the last surveyed line, water is moving through stone. It may pass through a narrow fracture no diver can enter. It may widen into a chamber no light has touched. It may carry traces of rain from last month, chemicals from the surface, food for cave animals, or clues from a climate thousands of years old. It may connect to another cenote, another system, another name not yet written on the map. The cave does not need to be mysterious in a supernatural way. It is already mysterious in the practical way that matters most. It is large, hidden, connected, fragile, and unfinished. It holds water people depend on. It holds evidence people have not yet read. It holds life adapted to darkness. It holds passages that may never be safely entered. And it waits, not dramatically, not impatiently, just as limestone and water have always waited, while the surface world slowly learns what has been beneath it all along. The next time the mind returns to the edge of a cenote, the water may look a little different. Not because the surface has changed, but because now the surface is no longer the whole image. Beneath it may be a mapped tunnel, beyond that, an unmapped one. Beyond that, a route only water can follow. The opening in the jungle is not the end of the story. It is one visible point in a hidden system still being written, one careful line at a time. And so, dear listener, we come back to the surface, though not quite the same surface we left. The cenote is still there. The trees still lean over it. The stone edge still drops away into clear water. A few leaves may be floating near the rim. A bird may call somewhere beyond the path. From a distance, it may look like a calm pool in the jungle, a place where people swim, take photos, cool off, and climb back into the heat with wet hair and a towel over one shoulder. But now the pool does not feel simple anymore. Now it has depth in more than one direction. Below the surface there may be a chamber, and beyond the chamber, a tunnel. Beyond the tunnel, there may be another cenote, then another passage, then a route mapped by divers with thin lines and careful notes. Somewhere farther on, the water may pass through a halocline, where fresh rainwater and salt water from the sea meet in a wavering blur. Somewhere deeper or farther away, a blind fish may move through the dark, sensing a vibration no human would notice. A shrimp may graze on microbial film. A bone may rest where it has rested for thousands of years. A ceramic fragment may sit in silt, still holding the fact that someone once carried it there with purpose. And beyond all that, there may be a passage no one has entered. That is the important part to keep. Not every unknown thing is loud. Not every mystery announces itself with a locked door, a hidden symbol, or a dramatic warning scratched into stone. Sometimes the unknown is just a dark opening at the edge of a mapped cave. Sometimes it is a water route too narrow for a diver. Sometimes it is a small difference in salinity, a chemical trace in groundwater, a pattern of sinkholes seen only from above, or an old bone found in a place that used to be dry. The Yucatan cenotes are not unexplained because science has failed to understand them. In many ways, science has explained a great deal. We know that limestone dissolves in slightly acidic water. We know that karst landscapes form caves, sinkholes, and underground drainage. We know that the peninsula's aquifer carries fresh water beneath the ground. We know that sea level rose and flooded caves that were once dry. We know that the Chicxulub impact left deep structures that still influence the region. We know that Maya communities treated many cenotes as powerful places connected with water, rain, death, and the world below. We know that cave animals can survive without sunlight by depending on surface material, microbes, and chemical energy. But knowing the main processes is not the same as knowing every passage. That is where the real wonder remains. The broad explanation can be true, and the local detail can still be unknown. A cave system can be mapped for hundreds of kilometres and still hold routes beyond the last surveyed line. A cenote can be famous, photographed, visited, and named, while the water moving beneath it still follows paths not fully understood. A human remain can be dated and studied, while the exact story of how that person entered the cave remains uncertain. An offering can be identified, while the words spoken when it was placed there are gone. A fish can be catalogued, while its small life in the dark continues almost entirely outside human attention. That is not a weakness in the story. That is the story. The water keeps its secrets not because it is hiding them in a magical way, but because it exists in conditions where answers are hard to earn. The caves are underwater, they're dark, they're fragile. Some are dangerous, some are archaeologically sensitive. Some lie beneath private land, roads, forests, towns, or construction zones. Some are connected in ways that are obvious to water but not to people. Some passages are too small, some are too silty, some should not be entered at all. In a place like this, mystery is not a decoration. It is the natural result of scale, danger, time, and care. And care matters here. It is easy to turn cenotes into a simple image: blue water, stone walls, a rope swing, a diver's light, a dramatic title. But these places are more than scenery. They are part of a freshwater system that people depend on. They are habitats for animals found in very few places. They are archives of ancient life. They are sacred landscapes with meaning for Maya history and for living communities. They are geological records tied to one of the largest impact events in Earth's recent history. They are also vulnerable. A cave can survive millions of years of slow natural change and still be harmed quickly by careless human decisions. Pollution can enter the aquifer. Wastewater can move through limestone. Construction can damage unseen voids. Tourism can bring attention but also pressure. Objects can be stolen. Bones can be disturbed. Sediment can be kicked up. A place that feels permanent may depend on choices made in the present. Stone is strong, but context is delicate. That is why the best way to think about the cenotes is not as puzzles waiting to be solved once and for all. They are systems that must be understood, protected, and revisited carefully. A scientist sampling water is not ending the mystery. A diver adding a line to a map is not conquering the cave. An archaeologist documenting a find is not taking ownership of the past. Each careful act makes the hidden world a little more readable, while also reminding us how much remains unread. There is something deeply human about that. We like clear endings. We like a final answer. We like to imagine that every tunnel has a last room, every map can be finished, and every strange place can eventually be put into a neat explanation. The Yucatan caves resist that. They give answers, but each answer opens another route. The limestone explains the sinkhole, the aquifer explains the water, the halocline explains the blur, the dry ice age caves explain the bones, the Maya underworld explains some offerings, the asteroid explains part of the ring. Then another question appears, not as an interruption, but as the next part of understanding. Where exactly does this passage go? How quickly does this water move? What remains beyond this restriction? Which species live only here? How did this object reach this chamber? What happens to the freshwater lens as the coast changes? What has already been lost before anyone saw it? These questions do not need to be answered tonight. Tonight, they can simply rest in the mind, the way the water rests in the stone. The point is not to turn sleep into homework. The point is to let the scale of the place settle gently. Above ground, a cenote may be the size of a quiet pond. Below ground, it may belong to a system large enough to change how a whole region is understood. That contrast is calming in its own strange way. It reminds us that the world is not limited to what is visible at eye level. Think back to the beginning of this journey. We started with an opening in the jungle, a pool that looked still, a question about what might lie beneath. From there, we followed the limestone as rainwater dissolved it over long spans of time. We watched hidden rivers move through a peninsula with few surface streams. We traced a ring of cenotes back to the buried structure of Chicxulub, where an ancient impact changed Earth's history. We entered Sakakton and the larger maze of flooded tunnels, where a map can grow after one confirmed connection. We crossed the halocline, that blurred layer where two waters meet. We looked carefully at bones and offerings, not as objects for shock, but as evidence that the caves preserve human and animal stories from very different periods. We paused with the Maya understanding of caves and cenotes as doorways to Xibalba and to sacred water. We noticed the creatures that live in the dark, pale and quiet, built for a world without daylight. Then we reached the unmapped passages, the places where the known line stops and the water continues. Now the circle closes, but the cave does not. The surface returns. The listener returns. The room around you is still here. Maybe the light is low. Maybe the house is quiet. Maybe the day has already loosened its grip a little, and somewhere far away from wherever you are, rain may be falling on the Yucatan Peninsula. It may land on leaves. It may run down tree trunks. It may soak into thin soil. It may slip into limestone cracks and begin the slow movement downward. No one on the surface may notice that particular drop of water. It may not seem important. But below ground, it joins the larger system. That is how these caves work. Not in grand gestures, but in accumulation. Drop by drop, crack by crack, passage by passage, bone by bone, map line by map line. A whole hidden world made from small actions repeated for longer than the human mind comfortably measures. And perhaps that is why cenotes stay with people after they leave. They are beautiful, yes, but many places are beautiful. What makes them different is the feeling that the visible pool is only a small part of the truth. You look down and you know, without needing to see the whole system, that something continues. The water does not end where your eyes stop. The cave does not end where the light fades. The story does not end where the map becomes blank. That feeling can be unsettling, but it can also be peaceful. There is relief in knowing that the world still contains places that require patience, places that cannot be rushed into simplicity, places where expertise matters, where caution matters, where listening matters. The cenotes do not ask to be solved quickly, they ask to be approached carefully. So maybe the next time you see a photograph of a cenote, it will not look like only a bright circle of water. Maybe you will imagine the limestone beneath it, pale and full of old roots. Maybe you will imagine the freshwater lens floating above the salt water and the halocline trembling where they meet. Maybe you will imagine a diver moving slowly through Sakyakatun, following a guideline through clear water. Maybe you will imagine the ring of cenotes across the peninsula, tracing the buried edge of an impact crater older than humanity. Maybe you will imagine a Maya offering sinking into a sacred pool. Maybe you will imagine a blind fish turning away from a faint vibration in the dark. And maybe you will imagine the unmapped passage beyond all of that. A low opening, a little flow, fine sediment on the floor, no footprints, no bubbles, no line, only water moving through stone. The cave does not need us in order to continue. That is worth remembering. Long before anyone mapped it, named it, feared it, swam in it, worshipped near it, or studied it, the water was already moving. Long after this video ends, it will keep moving. Rain will fall, the aquifer will respond, cenotes will reflect the sky. Some passages will be explored, others may remain unreachable. Some secrets will become data, some will remain in place, not because they are impossible to know, but because knowing them safely may take more time than we have given them. That is all right. Not every secret is a failure. Some secrets are simply the part of the world still waiting for careful attention. The Yucatan caves have already taught us about geology, water, extinction, migration, belief, ecology, and risk. They will teach more, but they will not teach on demand. They will teach slowly, in the language of maps, samples, bones, layers, flow, and silence. And so, dear listener, we leave the cenote as we found it, at least on the surface. The water is still, the jungle is warm, the stone edge is quiet, but now, beneath that stillness, there is a whole hidden landscape in the mind, a place of tunnels, chambers, ancient remains, living darkness, and water that has carried more history than any person standing at the rim could hold at once. If this quiet journey through the cenotes of Yucatan has helped you slow down, or if it gave your thoughts somewhere calm and strange to wander, I would be very grateful if you gave the video a like and subscribed. It helps this little space continue exploring the parts of science, history, and nature that are easy to miss when the world is moving too quickly. And if someone you know might enjoy drifting through hidden rivers, ancient caves, and gentle mysteries without being shouted at by the internet, sharing this with them would be a kind thing to do. For now, there is nothing more you need to solve. Let the maps stay open. Let the tunnels continue beyond the light. Let the water move through limestone at its own pace. Let the old offerings rest where they are. Let the small animals of the dark go on with their quiet work. Let the unanswered questions remain gentle. The cenote reflects the sky, but it also leads downward. That is the last thing to carry with you tonight. A calm pool can be an entrance. A stone well can hold a record. A hidden river can support a whole region. And in the dark below Yucatan, where fresh water meets salt water, and the mapped lines fade into blackness, the water keeps its secrets. Sleep well, fellow traveller. Wherever you are listening from, whatever time it is in your small corner of the world, may your thoughts settle gently now, and may the hidden places of the earth continue quietly beneath the surface, waiting for patient eyes, careful hands, and another soft light in the dark.